have 18, yeah. So it's 20 plus a 2-minute buffer. Just make sure to get mic'd up like 10 minutes before you talk.
Okay.
With the team back there.
Okay, sounds good.
Awesome.
Right, cool.
Oh, one other thing. There is a Ethernet hardwire cable in there if you need internet.
Oh, okay.
You can turn off your Wi-Fi, but
Got it.
if you don't need it.
Yeah, no, I got offline mode loaded.
Okay.
So.
Sick. Awesome. Love it. You go 2 minutes, I'll go
2:40 last session for 20 minutes.
Sick. I'm glad you guys have this up, because then I don't have to read from my phone.
Oh yeah, for sure.
Yeah, this helps.
Like, this is just projecting the full screen, right? Yeah. So if I exit the slideshow and do something. Oh. Okay, perfect. Cool. Sounds good. Yep. No. I think I have like a backup in case the Wi-Fi like goes down. Yeah.
This is the hard line, so not having issues at all.
Okay. Cool. All right. Well, thanks so much. We start in like 5 minutes, right?
5 minutes,
Yep.
yes. We're gonna start right
Yep. Cool. Is there an intro going on, or
Sorry?
is there an intro, or am I just going?
It's gonna be later.
Okay. Sounds good. Cool. Perfect. No, it's good. Thanks.
Whatever you want to introduce him, go ahead.
Yeah, we'll start at 11:15. Yeah, I told them 10 minutes before they present to come.
Perfect. Even better.
Chung and Calvin.
Amazing.
And then
Thank you.
Deanna and those folks, they also know to come 10 minutes early.
Perfect. Oh man, you're on top of it.
Try to be. I tried to.
Thank you, man. I appreciate it.
Was it as smooth the previous dates? Or was it a little bit more hectic?
No, actually, the previous days were actually pretty cool. The first date was a little bit
Hectic?
just a little bit, just because of the Wi-Fi issue.
Oh yeah, the Wi-Fi issues. Yeah. I told everyone you have a hardwire up there, but please download your slides if you have a video.
Just in case, yeah.
Yeah, just in case. Be wary for it.
Right, exactly. No, I mean, apart from that, everyone's good.
Perfect. We got a full room too. So appreciate you.
No. I showed some shit. That's okay.
give you a little extra time. Alrighty.
Actually do operations on top of the files, and it could be structured querying, right? Querying a more structured database to get aggregate insights over the types of data that you've extracted out. One top consideration when actually building this type of toolbox is complex documents. For those of you who follow our socials, we talk a lot about this type of issue where a lot of human knowledge in the form of like really complicated PDFs and other formats too. Embedded tables, charts, images, irregular layouts, headers, footers. This is typically stuff that's designed for human consumption and not machine consumption. And so, if the documents are not processed correctly, no matter how good your LLM is, it will fail. So we were probably one of the first people to actually realize that LLMs and LVMs could be used for document understanding. In contrast to more traditional techniques where you use kind of like hand-tuned and task-specific ML models to achieve kind of like document parsing over a specific class of documents, LLMs actually have a much general layer of accuracy that you can use to your advantage in just like understanding and inhaling any type of document with any type of complexity. Obviously, the baseline these days is you can just screenshot a PDF, feed it into ChatGPT or Claude. It doesn't actually give you amazing accuracy, but it's a good start. And so one of the kind of secret sauce, like magic tricks we found was figuring out how to interleave LLMs and LVMs with more traditional parsing techniques and adding kind of test time tokens in terms of agentic validation and reasoning to really get a higher level of accuracy. And so, we have a cloud service that does document parsing, and as a core step of this document toolbox, we basically benchmarked our modes where we adapt, Sonnet 3.5, 4.0, Gemini 2.5 Pro, 4.1 from OpenAI, and it basically outperforms all existing parsing benchmarks and tools out there in terms of open source to proprietary. So some of you might know us as a RAG framework. That's basically how we started. For those of you who don't know, we have this managed platform that is basically this GenAI native document toolbox. Contains a lot of operations that you need to do on top of your docs. It could be document parsing, document extraction, uses some of those kind of capabilities I just mentioned, and allows you to parse, extract, index data for all the set of tools I just mentioned. One of the special releases I actually want to highlight today, and we just announced this in a blog post a few hours ago, is Excel capabilities to help complement this document toolbox. A lot of knowledge work happens in Microsoft Excel and also Google Sheets and numbers, and basically it's spreadsheets, right? But it's been unsolved by LLMs. If you look at the document to the right, neither RAG nor text-to-CSV techniques will actually work over this because it's not really a structured 2D table. There's a bunch of gaps in the rows and gaps in the columns. So we basically built an Excel agent that's capable of taking unnormalized Excel spreadsheets and transforming them into a normalized 2D format, and also allows you to do agentic QA over both the unnormalized and normalized versions of the Excel spreadsheet. It's a pretty cool capability. I'll describe how it kind of works in just a bit, but it's going to complement our toolbox, right, in terms of more traditional document parsing, extraction, indexing, and it's available in early preview. So if you just take a look at the video, it's also on our blog post. We basically uploaded that example synthetic data set, transformed it into a 2D table, and you can also ask questions over it to basically get insights. And it's really doing the heavy lifting of deeply understanding the semantic structure of the Excel spreadsheet, and then using that and plugging that in as specialized tools to an AI agent. The best baseline is not really RAG or text-to-CSV. Those both suck. It's really just an LLM being able to write code. So LLM with the code interpreter tool is a reasonable baseline, gets you to 70-75% accuracy. Over like a private data set of synthetic Excel sheets, we basically were able to get this up to 95%. It actually surpasses human baselines of 90% of a human trying to go and do the data transformation by hand. A brief note on how it works. It's a little bit technical, but more details are in the blog post. First, we do some sort of structure understanding of the Excel spreadsheet. So we do a little bit of RL, reinforcement learning. We actually kind of adapt dynamically to the specific format of the document and learn a semantic map of the sheet. By learning a semantic map, we can then translate this into kind of a set of specialized tools that you provide to an agent. And so from an abstract perspective, you can kind of think about it as an agent could just write code from scratch. As LLMs get better, that will certainly become a kind of higher performing baseline. But in the meantime, we're helping it out by really providing a set of specialized tools over the semantic map so it can reason over an Excel spreadsheet. Great. The next piece here is, so we talked about a document toolbox. We talked about a lot of operations, basically make this document toolbox really good and comprehensive. So now that you plugged it into an agent, what are the different agent architectures and what are the use cases that are implied by them? As many of you probably know from building agents yourselves, agent orchestration ranges from more constrained architectures to unconstrained architectures. Constrained is basically you kind of more explicitly define the control flow. Unconstrained is like a React loop, function calling, code acts, whatever. You basically give it a set of tools and let it run. Deep research is kind of the same thing. For us, we basically noticed there's two main categories of UXs. There's more assistant-based UXs that can basically surface information and help a human surface information or produce some unit of knowledge work through usually a chat-based interface. It's usually chat-oriented, the input's natural language. The architecture's a little bit more unconstrained. You know, it's basically a React loop over some set of tools. And it's inherently both unconstrained, but also with a higher degree of human in the loop. So the goal is, or the expectation is that the human is supposed to kind of guide and coax the agent along the steps of the process to basically achieve the task at hand. I'm sure many of you have built these types of use cases, and so this is just a very small subset. But it's basically just your generalization of a RAG chatbot. There's a second category of use cases that I think is interesting, and I think a lot of folks are actually starting to build more into this space, which is this automation interface. So being able to actually, instead of providing some assistant or co-pilot to help a human get more information, processing routine tasks in a multi-step end-to-end manner. And usually the architecture is a little bit different. It takes in some batch of inputs. It can run in the background, or it could be triggered ad hoc by the human. The architecture is a little bit more constrained, which kind of makes sense, right? If you want this thing to run more end-to-end, you need it to not just go off the rails. And there's usually a little bit less human in the loop at every step of the process, and usually some sort of like batch review in the end. And the output is like structured results, integration with APIs, decision-making. After approval, it'll just go route to the downstream systems. Some of the use cases here include financial data normalization, data sheet extraction, invoice reconciliation, contract review, and more. I'll skip this video, but there's some fun example of some community-based open source repos we built in this area, like the invoice reconciler by Lori Voss. Kind of general idea that that has emerged and we've noticed as a pattern is, oftentimes the automation agents can serve as a backend because it runs in the background, can do the data ETL transformation. They're still human in the loop, but it's kind of doing the thing where it needs to process and structure a lot of data and do decisions in the background. And then assistant agents are kind of more front-end facing, right? And so automation agents can structure, process your data, and provide the right tool interfaces for assistant agents. Not every tool depends on agentic reasoning, but for a lot of these use cases, like for a very generalized data pipeline where you're processing a lot of unstructured context, you might have automation agents go in and process your data, provide the right tools for some sort of more research user-facing interface. So we talked about building a document toolbox. We talked about the different categories of agentic architectures and putting it together. Here are some real-world use cases of document agents. And these are basically examples of agents that actually help automate different types of knowledge work. So one of our favorite examples is a combination of both automation and assistant UXs for financial due diligence. Carlyle is one of our favorite customers and partners. They basically used some of the core capabilities that we have to build an end-to-end leverage buyout agent. It requires an automation interface to inhale massive amounts of unstructured public and private financial data Excel sheets, PDFs, PowerPoints go through some bespoke extraction algorithms with human-in-the-loop review. And then once that data is actually structured in the right format, providing a Copilot interface for the analyst teams to actually both get insights and generate reports over that data. If you look at any enterprise search use case that typically falls within the assistant UX, Cemex is one of our favorite customers in this space, where just being able to define a lot of different collections to different sources of data and providing more task-specific, specialized agentic RAG chatbots over your data, right? It's basically RAG, but you add like an agentic reasoning layer on top so that you can basically break down user queries, do research, and answer the question at hand. And on the pure automation UX side, we notice a lot of kind of use cases popping up around automation and efficiency. And so one example is actually technical data sheet ingestion. We're working with a global electronics company. They have a lot of data sheets that need to be automatically processed and reviewed. And historically, it's taken a lot of human effort to actually do this. So by creating the right end-to-end automation agent, you can basically encode the business-specific logic for parsing these types of documents, extracting out the right pieces of information, matching it against specific rules, and outputting the structured data into SQL. There's human-in-the-loop review, but if we're actually able to do this end-to-end, it transforms weeks of just like technical writer work into an automated extraction interface. So that's basically it. For those of you who are less familiar, Llama Index is the most accurate, customizable platform for automating your document workflows with Agentic AI. Our mission statement's evolved a little bit since the past few years. We're a very broad horizontal framework, oftentimes focused on RAG. But if you're interested in some of the capabilities, come talk to us, and then please come check us out at booth G11. Thank you.
All right. Thank you very much, Jerry from Llama Index. Next up, we have Chong and Calvin from Chong from LanceDB, and then Calvin from Harvey.ai, Scaling Enterprise-Grade RAG Systems, Lessons from the Legal Frontier. Give a big warm welcome to these two.
Audio. All right. Everybody hear us? Okay. Sounds like this is good. All right. Thank you, everyone. We're excited to be here, and thank you for coming to our talk. My name is Chong. I'm the CEO and co-founder of LanceDB. I've been making data tools for machine learning and data science for about 20 years. I was one of the co-authors of the Pandas library, and I'm working on LanceDB today for all of that data that doesn't fit neatly into those Pandas data frames.
I'm Calvin. I lead one of the teams at Harvey.ai working on RAG, tough RAG problems across massive data sets of complex legal docs and complex use cases. So yeah, our talk is about, one sec.
Maybe we should have used the other clicker.
Yeah. All right, that's okay. We'll use the laptop. So we're going to talk about some of the tough RAG problems on the legal frontier, sort of challenges, some solutions and learnings from our experiences working together on it. So we'll start roughly with like sort of how Harvey tackles retrieval, the types of problems there are, and then the challenges that come up with that, all with like retrieval quality, scaling, security, all that good stuff, and then how we end up sort of creating a system with good infrastructure to support that. So first of all, a quick intro to what Harvey is. We're a legal AI assistant, so we sell our sort of AI product to a bunch of law firms to help them do all kinds of legal tasks like draft, analyze documents, sort of go through legal workflows. And a big part of that is processing data. So we handle data of all different sort of volumes and forms. The sort of different scales of that are, we have an assistant product that's like on-demand uploads, same way you might like on-demand upload to any AI assistant tool. So that's like a smaller 1 to 50 range. we have these vaults, which are sort of larger scale project context. So if there's like a big deal going on that the law firm's working on, or like a data room where they need sort of all their contracts, all their litigation documents and emails in one place, that's a vault. And then the third is the largest scale, which is data corpuses, which are like knowledge bases around the world. So like legislation, case laws of a particular country, all the sort of laws, taxes, regulations that go into it. So yeah, some big challenges that come with that. One is scale, just very large amounts of data. Some of these documents are like super long and dense and packed with content. Sparse versus dense, I'm sure, is like a sort of retrieval challenge that all of you deal with, of how to represent the data, how to retrieve over it and index it. Query complexity is a big one. We get very sort of difficult expert queries, and I'll show an example of that in the next slide. The data is very domain specific and complex. There's sort of a lot of nitty-gritty legal details that go into it, so we have to like work with domain experts and lawyers to understand it and try to like translate that into how we represent the data, how we index, query, preprocess over it. Data security and privacy is a big one. A lot of this data is sensitive for like confidential deals or confidential, IPOs, financial filings, stuff like that. So we have to respect all that for our clients. And then of course, evaluation of how to make sure systems are actually good. So yeah, I'll show a quick demonstration of a retrieval quality challenge. So this is just on the query side of like, this is maybe the average complexity of a query someone might issue in our product. They're much more complex and maybe simpler ones, but this is right in the middle. And you can see that like there's a lot of different components that go into this. There's sort of well, to read it out, it's like, what is the applicable regime to covered bonds issued before 9 July 2022 under the Directive EU 2019-2062 and Article 129 of the CRR. So that's a handful. But what goes into it is like there's a semantic aspect. There's sort of implicit filtering going on of like, we want applicability before a certain date. There's a specialized data set being referenced, which is EU laws and directives. There's kind of keyword matches of like the specific regulation directive ID. It is multi-part in that it's sort of asking how this applies to two different regulations, like one directive, one article, and there's like domain jargon here, where this is like an abbreviation. I forget what it was, capital regulations, something. I looked it up this morning. But yeah, it's just very complex, and we sort of need a system that can tackle all this complexity and sort of break down this query and use all the appropriate technologies for the different parts of it. And yeah, so one common question we get sort of in response to this complexity is, how do you evaluate your systems? How do you make sure they're good? And that's actually where we spend a ton of time. It's not as much on the algorithms and the fancy agentic techniques, but more like how to validate them. And I'd say like investing in eval-driven development is a huge, huge key to building these systems and making sure they're good, especially when it's a tough domain that like you don't inherently know much about as maybe an engineer or a researcher. So I say there's no silver bullet eval, but we have like a whole range of them of like different task depths and complexities. So in sort of one dimension, you have it being sort of higher fidelity, but more costly, and then the other direction, it's like more automated evals that are faster to iterate on. So as an example, like the sort of high fidelity would be like expert reviews of just having them directly review outputs and analyze them and write reports. So that's like super expensive, but super high quality. And then maybe something in between is like an expert labeled like set of criteria that you can maybe evaluate synthetically or evaluate in some automated way. So it's still expensive to curate, maybe a little expensive to run, but more tractable. And then the third is sort of the fastest iteration, which is sort of more automated quantitative metrics like just retrieval, precision, and recall, sort of different, more deterministic success criteria of like, am I pulling documents from the right folder? Is it the right section? Do they have the right keywords in them? Things like that. And yeah, give you a quick sense also of sort of the scale and complexity on the data side, not only on the query side. So the data sets we integrate with are pretty massive. As you can see, we support like, data sets across all different kinds of countries, and for each one, there's sort of complex filtering and organization and categorization that goes into it. So we sort of work with domain experts for all of this, but also try to apply automation whenever possible, like use their guidance to maybe come up with heuristics or LLM processing techniques to be able to categorize all this. And I'd say that the performance implications are pretty significant as well. We need very good performance both online and offline. Online being like querying over this, you want good latency, and then offline being like ingestion, re-ingestion, running ML experiments for different variations and such. And I'd say generally one of these corpuses can be like, yeah, tens of millions of docs. So yeah, pretty large scale, and each document is often quite large. So I can talk quickly about the kind of infrastructure needs to support this. So at this scale, of course, we want the infrastructure to be reliable, available for all our users at all times. I'm sure that's something that all products need. We also want smooth sort of onboarding and scaling, where we definitely want our ML and data teams to be able to focus more on the sort of the business logic and the quality, and spinning up new applications and products for customers, and not too much about like the nitty-gritty details of the database or tuning that or manually scaling. And of course, there's always some in between where you want to have awareness of it. It can't be like fully 1000% automated. Likewise, we need sort of flexibility and capabilities around data privacy and data retention. Like I mentioned, with some storage needing to be like segregated depending on the customer, depending on the use case, sort of retention policies on some docs that we might only be allowed to store for certain amounts of time for legal reasons. We want good sort of telemetry and usage around the database. And then, of course, any sort of vector or keyword or any filtering database we want it to support good performance, query flexibility, scale, especially for all the different kinds of query patterns I mentioned before, where it's like you need exact matches, you want semantic matches, you want filters, you might want to navigate it, maybe, yeah, agentically or like in some dynamic way. So yeah, all that flexibility is important to us at scale. And that's where LanceDB comes in.
Cool. Thank you. Awesome. So, sorry. Okay, I'm going to try to hold this here maybe so there's no echo. Okay. Yeah. So, as I was saying, I work at LanceDB, and what we are delivering for AI is beyond what I call just a vector database, but what we call an AI native multimodal lakehouse. And so if you think about back to maybe Jerry's talk, right? In addition to search, you also need a good foundation, a good platform for you to do all of the other tasks that you need to do with your AI data. So this can be feature extraction, generating summaries, generating text descriptions from images, managing all of that data, and you want to be able to do that all together. So what you really need is sort of this lakehouse architecture where all the data can be stored in one place on object store. You can run search and retrieval workloads, you can run analytical workloads, you can train off of that data, and of course you can pre-process that data to iterate on new features that you can experiment for your applications and models. Specifically too, sort of in addition to these like large batch offline use cases, lakehouse architectures generally are good for that, but not necessarily for online serving. And this is where LanceDB, this distributed architecture comes in, and it's actually good for both offline and online context so that we can serve at massive scale from cloud object store. We can deliver cloud compute, memory, and storage separation. And we give you a simple API for sophisticated retrieval, whether you want to combine multiple vector columns, vector and full text search, and then do re-ranking on top of that. Those are all available with an API in Python or TypeScript that feels what folks have told me feels kind of like pandas or polars, like very familiar to data workers who are used to data frame-y type of APIs. And of course, for large tables, we support GPU indexing. So I think our record has been around something like 3 or 4 billion vectors in a single table that can be indexed in under 2 or 3 hours. So
all of that is to say, like, LandCB excels at massive scale, and this is happening at a fraction of the cost because of the compute storage separation and because we take advantage of object store. And so, of course, and I talked about sort of having one place to put all of your AI data. So this is the only database where you can put, images and videos and the audio track next to your embeddings, next to text data, next to your tabular data, time series data. You can put all of that in a single table. And then you can, of course, use that as the single source of truth for all the different workloads that you want to do on that data, from search to analytics to training, and of course, pre-processing or feature engineering. A lot of that is possible because of the open source Lance format that we built from the ground up. So, if you're working with multimodal data, whether it's documents, PDF scan slides, or just even large scale videos, if you're doing that in, let's say, like Web Dataset or Iceberg Parquet, you're missing out on a lot of features and things like lack of random access, or the inability to support large blob data, or not being very efficient about schema evolution. So Land's format, by giving you all of those, right, it makes it so that you can store all of your data in one place rather than split up across multiple parts. And so this is I would say, like the foundational innovation in LandCB, where without it, what we see a lot of AI teams doing is they have to have different copies of different parts of their data in different places, and they're spending a lot of their time and effort just sort of keeping those pieces glued together and in sync with each other. All right, so kind of to basically, you can think about Lance format as sort of Parquet plus Iceberg plus secondary indices, but for AI data. And that gives you fast random access, which is good for search and shuffle. It still gives you fast scans, which is so good for analytics and data loading and training. And it's only one out of this set that is uniquely good for storing blob data, or more importantly, a mix of large blob data and small, like, scalar data. And by using Apache Arrow as the main interface, Lance format is already compatible with your current data lake and lakehouse tools. So you can use Spark and Ray to write very large amounts of Lance data in a distributed fashion very quickly. You can use PyTorch to load that data for training or fine-tuning. You can certainly query it using tools like pandas and polars. All right, so what should we take back?
Yeah, so we back? Okay, so just wanted to share some general take-home messages about building RAG for these sort of large-scale domain-specific use cases. So the first is that these domain-specific challenges require very creative solutions around understanding the data and also choosing sort of modeling and infrastructure around that. Like I mentioned about trying to understand the structure of your data, what the use cases are, what the explicit and implicit query patterns are. So definitely spend time with that, work with domain experts, and try to sort of immerse yourself as much as possible in that. The second is to make sure you're building for iteration speed and flexibility. I think this is a very new technology, very new industry, and a lot of things are changing. New tools are coming out, new paradigms, new model context windows, and everything. So you kind of want to set yourself up for flexibility and iteration speed. And you can kind of ground that in evaluation, where if you have good evaluation sets or either procedures or automation around that, then you can iterate much faster and just get good signal on whether your systems are good or accurate. So definitely invest time in the evaluation to enable that iteration speed. And then, yeah, the third, which Chong covered, is that new data infrastructure has to recognize that there's sort of this new world we're entering with multimodal data, a lot heavier on vectors and embeddings. Workloads are very diverse, and the scale is just going to keep getting larger and larger as we try to sort of ingest and query over all the data that exists, public and private. So yeah, thanks for listening to our talk. Yeah,
We're good.
on the Harvey front, you can visit us at Harvey AI. Come talk to us or work with us. We're hiring if you're interested.
Thanks, everyone.
Awesome. Thank you so much, Chong and Calvin. Really exciting stuff. I think Harvey is changing, the legal space, and Lance is allowing you guys to do that at scale. So thank you so much. All righty. Okay, next up, we have Julia Niagu, Deanna Emery, both from Quotient AI, along with Maytar Asher with Tavali. Tavili, sorry, I always mess that one up. But we're super excited for these three speakers as well. So this one will be about evaluating AI search, the frameworks, for augmented AI system. So give them a big, warm round of applause.
Hello. Hey, nice to meet you. Sorry. Oh, thanks so much. Good to meet you, Chris. We have New York and San Francisco. So most of I'm in San Francisco. Yeah, so we'll work out of here. Often, yeah. Try to break it down into like a plan, like a query plan, and just what the different tasks, I suppose. Yeah, we'll do that. And then in the past, those like past jobs and stuff, that would often be manual, like you might write heuristics or do language parsing, but now the large language models can sometimes do that breakdown for you. Yeah. Yeah. Yeah, for sure. Yeah, thanks for stopping by. Hello, I'm Calvin. Nice to meet you, Quentin. Yeah, for sure. Oh, sweet. That's okay. Same domain's okay too. Yeah. Oh, let me get this off. I think.
Are you okay with just mirroring?
I do want to know.
View, does it not? And just turn off the screen mirroring.
I'm sorry?
Like if we do presenter view.
Yeah, if we're going to present a view, it'll extend it.
Oh.
And it won't
Can I try?
go into the actual.
Yeah, I want to use that.
There you go, perfect.
Okay.
If we can
Yeah, just drag the thing in there.
Where is
drag
it?
it on.
Like, yeah, I think that should work. There you go. And just make sure the slides switch. But it's not full screen.
And you can remove
The green thing.
You guys see that?
I don't see it.
Full screen on there?
It's like says full screen.
Can I try?
I think it's.
Oh, it was full screen.
Just leave it without. I think it's fine. We can do that. It's fine in the browser.
In the browser like that?
Yeah, that's okay. It's okay.
Okay.
Are you guys okay with that?
Mhm.
Okay, so good.
Thank you so much for coming. My name is Julia. I'm CEO and co-founder of Quotient AI.
I'm Deanna Emery. I am founding AI researcher at Quotient AI. My name is Leitara Sher. I'm head of engineering at Tavili.
And today we are going to talk to you about evaluating AI search. So let me start with a fundamental challenge we're all facing in AI today. Traditional monitoring approaches simply aren't keeping up with the complexity of modern AI approaches. First off, these systems are dynamic. Unlike traditional software, AI agents operate in constantly changing environments. They're not just executing predetermined logic, they're making real-time decisions based on evolving web content, user interactions, and complex tool chains. These systems can also have multiple failure modes that happen at the same time. They hallucinate, retrieval fails, they make reasoning errors, and all of these are interconnected. A little bit about what we do at Quotient. We monitor live AI agents. We have expert evaluators that can detect objective system failures without waiting on ground truth data, human feedback, or benchmarks. A year ago, we met Rotem, Tavili's founder and CEO, and he posed us with a problem that really crystallized the core issues we needed to solve. Here's the challenge. How do you build production-ready AI search agents when your system will be dealing with two fundamental sources of unpredictability you cannot proactively control? Under the hood, Tavili's agents gather their context by searching the web. The web is not static. Traditional benchmarks assume stable ground truth, but when you're dealing with real-time information, ground truth itself is a moving target. Your users also don't stick to your test cases. They can ask odd, malformed questions. They have implicit context they don't really share, and you're not aware of. And this is not just a theoretical problem. Tavili processes hundreds of millions of search requests for its AI agents in production. And they need a solution that worked at scale in these real-world conditions. And this is a story of how we built that.
Yes, so at Tavili, we're building the infrastructure layer for agentic interaction at scale, essentially providing language models with real-time data from across the web. There are many use cases where real-time AI search deliver values, and this is just a few examples of how our clients are using Tavili to empower their applications. Beginning from a CLM company that built an AI legal assistant to power their legal and business team with instant case insight, to a sports news outlet that created a hybrid RAG chat agent that delivers scores, games, and news updates, to a credit card company that uses real-time search to fight fraud by pinpointing merchant locations. So as you can imagine, evaluating a system in this kind of vast, fast-moving setting is quite challenging. We have two principles that guide our evaluation. First, the web, which is our foundation of our data, is constantly changing. This means that our evaluation method must keep up with the ongoing change. Second, that truth is often subjective and contextual. Evaluating correctness can be tricky because what's right may depend on the source or the timing or the user needs. So we have a responsibility to design our evaluation methods to be as unbiased and fair as possible, even when absolute truth is hard to pin down. So the first thing to think about in offline evaluation is which data to use to evaluate your system. Static data sets are a great start, and there are many widely open source data sets available out in the web. Simple QA is one example. It's a benchmark and a data set from OpenAI that serve as a standard for evaluating retrieval accuracy. We have many leading AI search providers that use Simple QA to evaluate their performance. Simple QA is designed to evaluate the system ability to answer short, fact-seeking questions with a single empirical answer. Another widely adopted dataset is Hotpot QA, which evaluates the system ability to answer multi-hop questions where reasoning across multiple documents is required to retrieve the final answer. Datasets like Simple QA and Hotpot QA are a great start for evaluating your system. But what happens when you're evaluating real-time systems that, especially when measuring that your system keeps up with rapidly evolving information and avoiding regression, like where we operate. Also, those kind of static data sets don't address the challenge of benchmarking questions where there's no one truth answer, where subjectivity is involved. This is what led us to think beyond static data sets towards dynamic evaluation that reflects the changing, the pace of the web, essentially. Dynamic data sets are essential for benchmarking RAG agents in real-world production system. You can answer today's questions with yesterday data. Dynamic data sets have real-world alignment. They have broad coverage, as you can easily create eval sets for any domain or use case that is relevant to your specific needs. And they also ensure continuous relevancy because they are regularly refreshed, which means that your system is always evaluated against the latest data. This led us to build an open source agent that basically build dynamic eval sets for web-based RAG system. It's open source, and we encourage everyone to check it out and contribute. And I also want to acknowledge the work of Eyal, our head of data at Tavili, who initiated this project a couple months ago. As you can see here, an example of a data set generated by the agent. It generates question and answer pairs for targeted domains using information found in the web. So the agent leverages the LangGraph framework, and it consists of these key steps. First, it generates broad web search queries for targeted domains, which essentially let you create eval sets for any domain of your choice and specific need of your application. The second step is to aggregate grounding documents from multiple real-time AI search providers. We understand that we cannot just use Tavili to search the web on specific domains, find grounding documents, then generate question and answer pairs from those documents, and then evaluate our performance on those documents. That's why we use multiple real-time AI search providers to both maximize coverage and minimize bias. The third step, which is the key step in this process, is to generate the evidence-based question and answer pairs. And we ensure that in the generation process, the agent is obliged to generate answer context, which also increase the reliability of our question and answer pairs and reduce hallucinations. You can always go back and check which sources were used and which evidence from those sources were used to generate each question and answer pair. And lastly, we use LengthMist to track our experiments, which is a great observability tool to manage these offline evaluation runs and see how your performance at different time steps. The next steps that we want to address is to support a range of question types, both simple fact-based questions and multi-hop questions similar to the hotpot QA. We also want to ensure fairness and coverage by proactively addressing bias and covering a wide range of perspective for each subject we generate question and answer to. Additionally, we want to add a supervisor node for coordination, which proved itself to be valuable, especially in these multi-agents architectures. And this will increase the quality of our question and answer pairs. The next step to think about is benchmarking. And we argue that it's important to measure accuracy, but you should not stop there. You should ensure an holistic evaluation framework, which use benchmark, like for our case, that measure your source diversity, your source relevancy, and hallucination rates. It's also important to leverage unsupervised evaluation methods that remove the need for label data, which enable to scale your evaluations and address the subjectivity issue. With that, I'll pass it over to Diana, who will explain more about these reference-free benchmarks and also share results from an experiment we ran using a static and a dynamic data set that was generated by the agent I described before.
So we performed a two-part evaluation of 6 different AI search providers. The first component of this experiment was to compare the accuracy of search providers on a static and a dynamic benchmark in order to demonstrate that static benchmarking is not a comprehensive method for evaluation of AI search. The second component was to evaluate the dynamic dataset responses using reference-free metrics. And we compare these results to the reference-based accuracies that we get from the benchmark in order to demonstrate that reference-free evaluation can be an effective substitute when ground truths are not available. So jumping right in, for our static versus dynamic benchmarking comparison, we use simple QA benchmark as the static dataset, and we're using a dynamic benchmark of about 1,000 rows created by Tavili. And as you can see here, both datasets have roughly similar distributions of topics, and this helps to ensure a fair comparison and diversity of questions. To evaluate the AI search provider's performance on these two benchmarks, we're using the simple QA correctness metric, and this is an LLM judge which is used on the simple QA benchmark. It compares the model's response against a ground truth answer in order to determine if it's correct, incorrect, or not attempted. And so here we're showing the correctness scores from that simple QA benchmark compared against the dynamic benchmark. And we've anonymized the search providers for this talk, but I do want to call out that the simple QA accuracy scores here are all self-reported, and so they don't all necessarily have clear documentation on how they were calculated. But as you can see, the correctness scores are, for the dynamic benchmark in blue, are substantially lower. And not only that, the relative rankings have also changed pretty considerably. For example, provider F, all the way on the end of this plot here, performs the worst on simple QA, but it performs the best on the dynamic benchmark. Looking a little closer to the results, while this simple QA evaluator is useful, it's certainly far from perfect. I have a few examples here of model responses that were flagged as incorrect by this LLM judge. But if you look at the actual text in the model outputs, they do contain the correct answer from the ground truth. On the flip side of things, here is an example where the LLM judge classified it as correct. And yes, you can see that the correct answer is in this response. But while the correct answer might be present, that doesn't necessarily mean that the full answer is right. This evaluation is not accounting for any of the additional text in this response, and there might be hallucinations in there, and that would invalidate it. So ultimately, this evaluation falls short of identifying when things go wrong in AI search. So what are some other ways that we can identify when things go wrong? Up to this point, we have been talking about a reference-based approach to evaluation. But what if we don't have ground truths? In most online and production settings, this is typically the case, and as we've already discussed, it's especially so in AI search. So the question is, can reference-free metrics effectively identify issues in AI search? For this talk, we're going to look at 3 of Quotient's reference-free metrics. We'll look at answer completeness, which identifies whether all components of the question were answered. So it classifies model responses as either fully addressed, unaddressed, or unknown, if the model says, I don't know. Then we'll look at document relevance, and this is the % of the retrieved documents that are actually relevant to addressing the question. And then finally, we'll look at hallucination detection, which identifies whether there are any facts in the model response that are not present in any of the retrieved documents. And so we use these metrics to evaluate the search provider's responses on this dynamic benchmark. So we've got answer completeness plotted here. The stacked bar plot shows the number of responses that were either completely answered, unaddressed, or marked as unknown. And If we look back at the overall rankings that we saw earlier on the dynamic benchmark, you can see that the rankings from answer completeness pretty closely match. The average performance scores for the two get a correlation of 0.94. So this indicates that the reference-free metric can capture relative performance pretty well. But completeness is still not the same thing as correctness. And when we have no ground truths available, then we have to turn to the next best thing, and that is the grounding documents. So this is where document relevance and hallucination detection come in. Both of these metrics are going to be looking at those grounding documents in order to measure the quality of the model's response. Unfortunately, of all of the search providers we looked at, only 3 of them actually return the retrieved documents used to generate their answers. The majority of search providers typically only provide citations, and these are largely unhelpful at scale and also really limit transparency when it comes to debugging. So these are those document relevance scores for the 3 search providers, and they've been re-anonymized here. The plot to the left shows the average document relevance, the percent of retrieved documents that are relevant to the question, and the plot to the right shows the number of responses that have no relevant documents. And if we consider these results in conjunction with answer completeness, we find that there's a strong inverse correlation between document relevance and the number of unknown answers. And this kind of matches intuition. If you think about it, if you have no relevant documents for the question, the model should say, I don't know, rather than trying to answer it. And so this brings us to hallucination detection. And here we were actually surprised to see that there was a direct relationship with the hallucination rate and document relevance. Provider X here has the highest hallucination rate, but it also had the highest overall document relevance. And this is kind of counterintuitive. But if we think about it more, provider X had high answer completeness, the lowest rate of unknown answers, and it also had the highest answer correctness from the benchmarking earlier of these 3 providers. So this probably implies that maybe in provider X's responses, they're more likely to provide new reasoning or interpretations in their response, or maybe even they're more detailed and thorough, and this just creates more opportunity for hallucination in their responses. But the point I want to make here is that when considering these metrics, depending on your use case, you might index more heavily on one over another. They're measuring different dimensions of response quality, and it's often a give and take. If you perform really well in one, it might be at the expense of another. And as we see here, there is a trade-off between answer completeness and hallucination. But also, if you take these 3 metrics in conjunction, you can use them to understand why things went wrong and identify potential strategies for addressing those issues. This diagram here shows a few examples on how you can interpret your evaluation results. How you can interpret your evaluation results to identify what to do to fix it. So we've got one example here where maybe your response is incomplete, but you have relevant documents, you have no hallucinations. So this probably means you don't have all the information you need to answer the question. And so just retrieving more documents might solve that. But the big picture idea is that your evaluation should do more than just provide relative rankings. It should help you identify the types of issues that are present, and it should also help you understand what strategies to implement to solve those issues.
Okay, so in conclusion, let me just quickly paint a picture of where we're heading with all this, because this is not just about building the agents we've been building for the past couple of years and then slapping evaluation on it and then continuing to do the same thing. It's not about building better benchmarking, it's not about better monitoring, it's not about better evaluation. It's about creating AI systems that can continuously improve themselves. And imagine for a second that agents don't just retrieve information, but learn from the patterns of what information is outdated, what sources are unreliable, and what users need. They can also maybe detect hallucinations mid-conversations and correct the course, all without human intervention. And this framework that we shared today, dynamic data sets, holistic evaluation, reference-free metrics, are the building blocks for getting there. And this is where we want to get with augmented AI. So thank you so much for your time.
All right, Tengyu Ma, are you in the room? Our next speaker. Tengyu Ma from MongoDB. Oh, you are? Okay, perfect. Come on up. All right, thank you very much from Quotient AI and Tvili for presenting. Next up, we have MongoDB, so you know them. They're very much in the ecosystem. Tengyu Ma will be presenting RAG in 2025, so what's changed? State of the art and the forward road. So he'll talk about kind of the roadmap debate, RAG versus fine-tuning versus long context. And then, secondly, RAG today, the benefits, challenges, and current solutions. And then what will the future of RAG look like? So, all right, while he's getting mic'd up, we'll let him get settled in. But big round of applause for Tengyu Ma from MongoDB.
Is this working? Okay. I guess yeah. Thanks for coming. Thanks for having me here. I'm Tengyu Ma. I was the CEO and co-founder of Voyage AI. We just recently got acquired by MongoDB. I'm also teaching at Stanford as well. So this is about RAG, which is the main focus of Voyage AI, the startup who is focusing on how to make retrieval better. So, but I will just generally talk about RAG and we'll touch on some of the products we make as well, very quickly. So I guess why we are doing RAG or anything like that, right? So I guess the main reason is that large language model or these days agent, which are using large language models as well. If they out of the box, they cannot just have proprietary information from many of the companies, right? Because if they know anything about what MongoDB, for example, internally has, then the data was leaked. So that means that if you want to apply any of this to enterprise, then you need to ingest a lot of data from the proprietary information. So I'm going to discuss, which kind of technologies to enable us to ingest the data. I guess there are a few options: RAG, fine-tuning, and long context, which are all ways to ingest data. And I'll focus on RAG for the rest of the talk. So I guess for this audience, probably most people know these technologies. They are all very simple on high level. So for long context, it's just the most simple. You just dump all your documents to a large language model's context, and maybe it's like 1 million tokens, maybe it's 1 billion tokens. And then you have a query, and you just get a response. Fine-tuning is like you first fine-tune a large language model, you update the parameters, and then you say, I'm not going to look at the documents anymore. When the query comes, I just use the updated parameters to generate a response. And RAG is also pretty simple. So basically what happens is that on the fly, you use the query to retrieve some subset of the documents. You use the retrieval or search method. And then you get some relevant documents. You give this small set of relevant documents to the large language model, and then you generate a response based on those contexts. So this is my one slide, kind of like a summary of how I think about the differences between these technologies. Some of these are inspired by some of the research at Stanford. When we kind of started to build Voyage, we kind of like believe in RAG, and one of the reasons is that we don't believe that fine-tuning can work, and long context, I think, I also don't really believe that it can be cost efficient in the long run. So basically, I think the way that I think about this is that I try to make an analogy to how humans are learning from or using the additional proprietary information. So in some sense, long context is kind of like you skim an entire library to answer any single question, right? Every time you answer a question, you need to go through the entire library, which has like probably 1 billion tokens. And fine-tuning is kind of like you read this library in advance, you muscle memorize them, you try to internalize them in your brain, in your neurons, in your synapses, and you update your brain, basically rewire your brain so that you really know all of those deeply. The challenge there is that it's very difficult and somewhat unnecessary because you cannot really memorize all the books in the world, and memorizing a subset of them sometimes is kind of like which subset you want to memorize is kind of tricky as well. So and another thing is that it makes forgetting the knowledge also tricky because you don't know which part of the knowledge you should forget and how to cleanly forget all of them. And also this makes the access, the data governance also kind of tricky because maybe there are so many libraries, so many books in the library, and not everyone can access everything, and how to organize those. And on the other hand, RAG is very, very simple and modularized, as I've shown. So and very reliable and also kind of fast and cheap. So and it's kind of like similar to how humans actually are using the libraries, right? You retrieve the most relevant book chapters or book chapters, and then answer the question. It's kind of a hierarchical way to store your information, right? You don't really put all of the information in your brain. You put them in a library and then you use them when you need it. So that's why I believe in RAG, and this is kind of how you implement the retrieval part. So basically, there is a breakdown of two components. Actually, there are three, if you are advanced. So this embedding models which vectorize the documents and query into vectors, and the vectors are representations of the this kind of like representations of the content or the meanings of the documents and queries, and then use the vector database to store the data and also search with a k-nearest neighbor search in the vector space, and then you get the relevant documents, and then you can use large language model to generate answers. So we have seen significant improvements over the retrieval accuracy in the last 2 years. When we started Voyage, I think OpenAI v3 was not yet launched. OpenAI v3 was launched 1.5 years ago, and in the last 1.5 years, Voyage, has made significant progress. Cohere also made some progress. So we can see that the new model has much better accuracy and with lower cost. Generally, we have much better scaling law, right? So the same number of parameters, the quality becomes better, or the same quality, the parameters become smaller and it becomes cheaper. And all of these are through kind of like optimizing the research stack, the training stack, as much as possible, all the way from like data curation, data selection, architecture, loss functions, evaluation, so on and so forth. And we still, believe that there's a big headroom here because right now you can see that in this plot we are averaging over about 100 data sets, and the accuracy is about 80%. So that means that you still have like probably 20% of the improvement headroom. But that said, just to be clear, it's not like for every data set you only have 80% accuracy. For probably half of the data sets, the accuracy is probably 90% or even 95%. And for some of the other ones, it's kind of 60, sometimes 20, sometimes 30. So that's why in average it's 80%. So basically, I'm saying like for some of the tasks that are common, I think you can get already very high accuracy in the retrieval step. And another thing that Voyage and other companies has offered is this so-called matricial learning and also quantization aware training. So basically, these are two approaches to reduce the storage cost for the vectors. So basically, matricial learning means that you make sure that even you have like a high dimensional embedding, right? You can use a subset of the coordinates. It's usually the first, let's say suppose you have a 2048 dimensional vectors, and the first 256 dimensional sub vector is still a reasonable embedding. The accuracy wouldn't be as high as 2048, but it will be almost the same, maybe with a 1 or 2% loss. And quantization is kind of in a similar vein, so where you even you lower your precision of the vectors, you still get pretty high performance. And you can see the trade-off on the right of the figure here. So basically, you can save 100x, at least 10x without losing much. If you save 100x in the storage cost, then you start to lose probably 5 to 10%. But Voyage, is doing a great job here because you can save 100x, but still doing better than OpenAI. That's just because the parental frontier is different. So, And you can actually see better trade-off for domain-specific models, which I'm going to discuss in a moment. I have 9 minutes here, so I will probably just quickly go through some of the techniques that you can use. So basically, the next question is that how do you do better RAG, besides using better embedding models? Using better embedding models is probably one of the simplest way. So I'm just going to go through it quickly. So one of them is to use hybrid search and re-rankers. You can use lexical search and other kind of search, and then combine them with a re-ranker. And Voyage provides a re-ranker as well. And another one is you can enhance the queries and documents by the so-called query decomposition and document enrichment. So this is probably the most common one. Maybe let's spend 1 minute on it. So it's actually very simple. You just say, if you have a query RAG, then you try to improve the query by making it longer using a large language model. You can also decompose the longer query into small subqueries so that you can have like a few different queries and search for different subset of documents. And you can also enrich the document by adding additional meta information in it. You can add titles, headers, categories, authors, dates. Sometimes you trunk the document so that in the trunk you don't even have this information anymore. So that's why you have to add the global information into each of the trunks. And some of this global information can be added by large language models. Anthropic wrote a blog post which does achieve pretty good results. So basically they use large language models to generate additional context that you can add to the trunks so that you can make the trunks more informative, and then it's easier to search through them. So another one is you can use domain-specific embeddings where you customize embeddings for certain kind of domains. In MongoDB or Voyage, we customize it for code, for example, and you can see that you get much better performance, and also it's a better trade-off in terms of the storage cost and accuracy. So basically, you don't lose as much if you compress the vectors even further. So here we lose probably 5% by compressing for like about 100x, but before we lose probably 10% or 15%. Fine-tuning is another one. You can fine-tune embedding models with your own data, and you can also use other, sometimes I call them tricks, on top of the embeddings, right? So these are different type of ways to retrieve using additional information like graph, iterative retrieval, so on and so forth. They're all based on embeddings, but you can use the embeddings in many different ways as an additional layer. I guess I'll use the next probably 5 minutes to discuss some of my vision for how RAG will go in the future. I do believe that RAG will be there forever because this is, as I argued in the first slides, the first set of slides, this is the kind of like very similar to how humans are using additional large amount of data. You retrieve, you hierarchically select some subset, and then you use those to answer the questions or take some actions. And this is very efficient because you only use a small subset of the data. Regarding how RAG will evolve from a technical point of view, I like to draw some analogy from how the AI generally is evolving. So I think I was reflecting on when I was teaching at Stanford, started to teach at Stanford about 7 years ago. I started to teach with Chris Ray this machine learning course. And one of the slides literally have these 7 steps on how do we build ML systems in enterprises. So this slide is still in the lecture notes. We still teach them, but just with more kind of like asterisks around it. So you can see like you need to go through many steps, collecting data, train, test, split, define your loss functions, build models, and iterate and repeat. And then for the large language model world, it's kind of like this, right? You don't need to do any of this. You just take a large language model out of the box and just you can deploy it in enterprise in most of the cases. Of course, it's not going to be perfect, but this is already better than in the old days. You do all of these steps in the enterprise using all the enterprise data. Just out of the box, you are doing already very well. Of course, you still have this issue that you cannot, the out of the box large language model cannot access proprietary information. Then you can use RAG for it. So, but I think the point here is that before, all of these steps have to be done by the kind of like the users or the enterprise or the customers in some sense. And now you, largely speaking, just can take off-the-shelf components and connect them and build your AI applications very fast without going through these training steps. The trainings still have to be done, right? All of these steps still are done, but they are done by OpenAI, Anthropic, or Voyage, MongoDB, the providers of the models. But now the users, the end users. So, and I think for RAG, I would say probably the same kind of evolution should happen. So right now, what happens is that we have the several different layers where you have the computing infrastructure layer about the GPUs, or some of the KNs on the CPUs, and there's also a model layer where you have the embedding models, the rerankers, the large language models, and then on top of all of this, people use a lot of I call it tricks to make RAG accuracy much better. Right? You can use all kind of parsing strategies. You can use all kind of trunking strategies. You can do some recursive search. You can do some contextual trunks, graph RAG, so on and so forth. Right? That's what happens right now, and it's kind of necessary. These tricks are somewhat necessary because the embeddings and rerankers and large language models, none of them are perfect yet. Right? So, but I do believe that in the future, I think this model layer will grow. And the tricks will be smaller. So it's going to be fewer and fewer tricks, and the models can capture many of the performance gain by the tricks. I think we have seen this in the large language model space as well, right? So 2 years ago, I think you need to do a lot of things on top of the GPT-3 to make your application work. And now, even out of the box, you can get the same performance as before with all of the tricks. Of course, you still probably need some kind of tricks because some information are not some information the embedding models and rankers don't have just, right? So the general purpose models or off-the-shelf models don't have certain information, and then you can incorporate those into your tricks. For example, one thing that is that the definition of the similarity matrix could be something that you should customize in your prompt. And in this one, I think there are several things that we are developing towards this vision, right? So one of them is multi-model embedding. This is to dramatically simplify the workflow so that you don't have to do many things, right? So these days, the multi-model embedding provided by Voyage can just take in screenshots, right? Before you take a PDF, you have to do the data extraction to turn them into image and text, and then probably do some embeddings for the image and embedding for the text separately. And parsing this PDF is actually complex, and for videos, you have to turn them into transcript, and then use the text embedding, so on and so forth. Right now we have the multi-model embedding, which just takes in screenshots. You can deal with PDF, PPT, PowerPoint, any of the other kind of slide stack in the same way. Just take a screenshot and then use the multi-model embedding. We don't have we can even do the same thing for video, not necessarily the perfect way, but you just take screenshots of the frames, consecutive frames, and you give it to the multi-model embedding, and you can turn them into vectors, and you can search over those documents or videos or slide stack. So, and these are some performance metrics that we have evaluated. We have tried oh, by the way, another one application is tables, right? Now you can just take a screenshot of the tables. You don't have to think too much about what is the header, what is the row, so on and so forth. And we have done evaluations on many of these document screenshots, table figures, and also text only. And you can see that it's improving across the board. So the final one I would like to mention, which is something that we're going to launch soon, is that this context-aware and auto-trunking embedding. So right now, what happens is that when you have a long document, you do have to trunk the data. One of the reasons is that the context length of the embeddings is limited. If you have 100K tokens, you do have to trunk it into 3 or 4 trunks. Even though Voyage AI has we have the longest context window is still 32K. So that's one reason to trunk. And another reason to trunk is that sometimes it's the long document, even you don't trunk. Suppose you can have a way to put all of them in a context window. Still, when you retrieve, you're going to retrieve on a document level. Then you retrieve a very, very long document. And then you should give this long document to large language model. It's going to be very, very expensive, right? If you give 100K tokens to large language model, every time you answer any question, if you do some cost analysis, you'll find that that core is very, very expensive. So that's why you do have to work on a smaller unit so that you can cut the cost and be also more focused, right? So sometimes you give a long document to large language model, it misses some of the context in the middle, and you have to use the retrieval to focus on a paragraph, a page, so on and so forth. So that's what happens right now with the trunking. And but all of these are done by the users. And our vision is that we're going to do this for you, and also we're going to get all the meta information from other trunks. So basically, In a nutshell, the interface will be that you give us a long document, and we're going to trunk it for you, and then also we return the trunks and also the vectors for each of the trunk. And each of these vectors is not only representing that trunk, but also representing some of the global meta information from other trunks. So it has all the details of the corresponding trunk, and also has some kind of like a cross-grid information from other trunks, so that you can get the best of the both worlds. That's what I'm going to launch soon. And another one is that we're going to have some fine-tuned API at some point to make you so that you can fine-tune with your own data. I guess it's exactly time. Thanks very much.
Alrighty, folks, that's it for the first block. Enjoy lunch. Come back around a little bit before 2. We'll start with the second set of sessions. We've got EXA 11X as well as Google, so don't miss it.
3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Testing 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. All right. Hey Nadia, can you bring up the DI? The DI for the audio? Share the.
Oh, it's number 7. Number 7.
DI right there. Yeah. Get up.
You can't pinpoint focus or draw it closer. Even yelling why you betray me like this.
Can you switch? Give me 1 second. I'm just double checking the screens here. Can you go ahead and go into slideshow?
folks come. We'll get started in like 4 minutes. It's 20 minutes flat, so we'll be good on time.
You have some leeway.
Okay.
You can go over.
Sweet.
Don't be too stressed about it.
Check, check. How we doing, y'all? We're about to get started in just about 2 minutes. Feel free to grab a seat. Raise your hand if there's a seat next to you. We have a bunch of folks in the back looking for seats. If anyone's in the back, you want to find a seat, you can find a seat next to these folks raising their hands. Let's pack it in. It's going to be a full room. The last time we did this at the last AI Engineer Summit, we ended up by the end of it having the full ring around with people standing. So if you want to get a clear view, please grab a seat. And then we'll get started. And then we'll get started in just about 2 minutes. Thank y'all. Sweet. Speakers, if you can bring it in real quick. My guy.
Clearly not reading the room.
Check, check. 1, 2, check, check. 1, 2, check, check. 1, 2. Sweet. About to get started here. How we doing, everyone? All right back there? Okay, seems like the mic just kicked on. Can you hear me all right back there? In the back? Yeah? Sweet. Raise your hand if you flew in and you live outside of San Francisco. Holy shit, who came the farthest? Where'd y'all come from? UK? I don't think that's the farthest. Poland, we're getting pretty far. Bangalore, anyone got Bangalore beat? That's hard to beat. Romania. Brazil. I think Brazil's a little bit closer. Calcutta. Oh shit. One more back there. Melbourne. Shit. Wow. This is crazy. Y'all, and if you're back there in that corner, if y'all can slide over a little bit, because there'll be more people joining as we're going. So just slide over this way so we make more space so that people can actually see. We're about to get started here. So I'll introduce myself real quick. I'm Dave Fontenot, the founder of HF0. For those of you who don't know, HF0 is the most selective startup program in the world now. It is the program for repeat founders. A lot of the founders that you're about to see on this stage have built billion-dollar companies before this, and then they're starting their next company, and they're building something really interesting, mainly in AI. It's a 12-week residency where you move into this residency, and you give up everything in your life. Everything in your life. And you just go all in on birthing your life's work. And without further ado, let's give it up for the first startup in this series that we're calling the Next AI Unicorns. Let's give it up for Diego from Korea.
Test. Cool. Hello, everyone. My name is Diego Rodriguez. I am co-founder and CTO at Korea. We're building an AI creative suite. I'm going to tell you 3 stories, and then I'll try to hire you. So a friend once told me, if you think about it, like cars are easy to predict, right? Like, it's like you get the horse, you have the wheels, you swap the horse, and you put an engine, which was known at the time, and that's the car. But like, you know what's really hard to predict? Traffic. So it's my job to ask, what are the traffics that we're missing, especially with AI? You know, YAML, JSON, MCP, whatever. It's like, okay, but like, what happens when you generate 1 million images per day like we do for one studio? How do you find that? Another story. Tower of Babel, we wanted to reach heaven. God was like, no, created a bunch of languages, and basically misunderstanding was like, nope, you're not gonna go there. And it reminds me of stand-up meetings where people are like, no, it should be React. No, but like it should be like JavaScript vanilla. It's like, dude, we're not, God is winning. You know? But now we have AI. So maybe, okay, here, if it wasn't with crypto, it was with AI, you'll see. And so this is only like people trying to convey ideas, and that's what we're trying to tell, just trying to tell stories. The final story is, I was talking with someone from Netflix, and she was like, what happens when we are making so much content personalized to each town in India? How do I even find that? Like, right? And then a few days ago, I just realized that Korea was already being used for broadcasting an ad with Fox to millions of people. And then I look, and they literally signed up 2 days ago. So we went from sign up to conversion to payment to broadcast in 2 days. And then this was the CTO telling me that. I was like, whoa. I'm about to run out of time. So the mandatory slide, a bunch of users, 25 million, raised a bunch of money. We did this with 8 people. Some of the people who are using us, an email that I created for today that is gonna prioritize applications. Thank you. Sorry.
All right, open home. Okay, everybody, the smartphone was the #1 best-selling consumer product last year, and the laptop was the second. Pop quiz for all you here. What was The third wasn't the Apple Watch, wasn't the AirPod. No, I think I heard it. It was a smart speaker. 500 million smart speakers were sold last year. But why do they still suck? You can barely talk to them. There's no customization. There's no community. There's nothing. That's why we built Open Home, the very first AI-driven smart speaker. And we're letting you guys build smart speakers too. And we believe here that the future is talking with AI. You should be able to talk seamlessly, intuitively. In fact, you shouldn't have to use this really awkward command-based language. You should be able to just chat naturally. So that's what we're building. And we're letting people here today build their own smart speakers and build them in whatever form that they want. And the key here is developer ecosystems. And well, we know developer ecosystems. I started my career as the chief of staff for the founder of Splunk, a $30 billion big data company. Then I was on the founding team of MakerDAO, a $5 billion developer ecosystem. My co-founder and I raised $50 million for our last business, a data privacy tool, and we sold that business, but it all came down to developers and really building what people actually wanted. And, well, oops. Now, with Open Home, we have over 10,000 developers building on Open Home. They're building all kinds of interesting things, all types of different custom smart speakers, building interesting voice AI applications. Sky's really the limit. And well, what do developers really want? They want open source, they want LLM driven, and they want fully jailbroken. They want Open Home, the AI smart speaker. And now what's really exciting is with voice AI, you can put it on any type of hardware. We have developers building talking toys, AI robots, AI appliances. You should be able to talk to the world around you in a much more natural way, and you can do that now with Open Home, an AI smart speaker. Here's our dashboard. We have many, many applications, hundreds of applications that have been built, games, personalities. We have an editor that you guys can go in and build, and all kinds of interesting things, home automation tools. And what's really exciting is our last dev kit got booked up within minutes. And today we have a special announcement for you guys here today. We're releasing the next batch of 500 dev kits for free for everybody here. If you guys want it, we will ship you a dev kit. It's very cool. You can build on it. You can talk with AI. You can build your own smart speaker here. And we're doing it today. Thank you so much.
One, two. All right. How's it going, y'all? I'm Josh. I'm the founder of a company called CoFrame, and I am missing my slides. Cool. I got it. So the last company that I started, we scaled to over $2 billion in the course of a couple of years. But when I started to tinker on using AI to generate code and created one of the actual top autonomous coding agents on GitHub, was number one on GitHub for a week, I realized it was time to build something bigger. The internet is dead. It's not adaptive. It's not personal. It's not truly living, in a sense. Websites are all one size fits all. And we're bringing that concept to life. We are giving websites a life of their own, giving every single customer experience its own AI growth team. But this isn't just a pipe dream. We made $20 million for Europe's largest travel company in just a few weeks. We increased click-through rate for India's largest company, a $400 billion enterprise, also in a few weeks. And how are we doing it? We're working with the best, and we have the best. We're the only marketing tech company that's partnered directly with OpenAI to date, and they actually called our team cracked, which is cool. So if you're interested in learning more about this, reach out. Thank you.
Hi, I'm Eugene. I'm sorry. My team is obsoleting all the AI models you see today. Because you see, my team built Quirky 72B, the world's largest model without the transformer attention with only 8 GPUs. And this allows us to have 1,000x lower inference on our new architecture while performing the same. Surprisingly, the techniques that the technology that we built can also be applied to existing transformer models through speculative decoding. Nothing too big, nothing too important. But here's my hot take. Scale is dead. And I'm not saying this just from my own opinion. Like, we are burning billions into making AI models bigger. But at the same time, the DeepMind founder and CEO is saying compound AI agents errors will take more than 10 years to fix. Yan LeCun is even saying that we need a new AI architecture to push the paradigm forward. And in production, we see over 90% of AI projects fail. The reason behind this is not something that scale can fix. The problem is reliability. The thing is, like, would you order and use an app that only succeeds 45% of the time? Would you order DoorDash that way? Of course not. If your order goes missing or you end up having 100 pizza, you're going to be stuck with customer support screaming down there. It's a frustrating experience. But that's what AI agents do. When they work, they're awesome. When they don't work, we are stuck cleaning up the mess. And that's even with frontier models. And here's the thing. What companies want is not a smarter model that can do PhD level math. The models are really smart enough. But what we actually really want is the models reliable enough to book airline tickets, sort out emails, or file our taxes and invoices. That's what we actually want. And that is what we are building at Featherless AI. We are a research lab that is building personalized AGI that's made reliable for each one of you. And most recently, we are in our research that we actually shown that we built an Action R1 agent that beats Claude 4 Sonnet and Gemini and OpenAI. This model is not going to do PhD level math, but it's going to fill up the form with absolute reliability better than the frontier. And that's the thing. Like, are we going to burn billions more to make a smarter model that is just a few percentage point higher IQ? Or are we going to make something that's 99.9% reliable for the boring things in life? Because this is where the money is for all of you. Because think of it, as AI engineers, reliability is revenue. For every use case you unlock and find, you're going to do a $1 billion app in e-commerce or in B2B sales, and that is something that all of you can build on, not rocket science. And that's what we are building, and if you're excited about it, feel free to reach out to us. I'm Eugene at feathers.com.
Test, test. Hello, everyone. My name's Jonas. I'm an engineer, and I like working with data. I love working with data, actually. I love it so much. I dropped out of high school when I was 15. I got on a plane. I moved across the country to California, and I joined a startup called Branch. You might have heard of it. Anytime you were clicking one of those links on your phone for an app, that was probably us. I also led a team there that built a search engine that over 100 million people used every day. And then last year, I left, along with one of the founders of Branch, to tackle an even bigger challenge. This is probably what you think your sales and marketing teams are doing with their budgets. And you wouldn't be entirely wrong. So that's why I co-founded Upside. We do forensic revenue attribution and intelligence. But what does that actually mean? Well, how many of you have an email from a salesperson like this sitting in your inbox right now? And how many of you are actually going to reply to it? Yeah, I didn't think so. These teams are shouting into the void, hoping something will work because they don't actually know what works. Because their data is a mess. I mean, don't get me wrong, they're data hoarders. They store everything, they stuff it in Salesforce, they treat it, it's basically a SQL database in a trench coat, but they're not data practitioners. They don't know what to do with it once they have it. But now we have things like LLMs. They can help with this. They can take that poor, mishandled, abused email record, and they can pull the most important details out of it into a structured form. And so just as search engines and web crawlers learned how to make sense of the unstructured web, Upside is turning raw enterprise data into a highly structured map of the world and all the interactions that people do in it. So there's hope. We can untangle this mess, and we can create a data command center that these teams can actually use to reach their customers more effectively. We only just started talking about this publicly a couple weeks ago. We've been quietly building in the background for the last year or so, and my co-founder decided to make a small post on her LinkedIn, just to update our network on what we'd been off doing and the things that we'd been building, and it blew up. Like, there's so much pain people feel around this, and they're hungry for a solution. We got a whole slew of demo requests coming in from people that want access to the product, and now we have a bunch of customers lining up that want to get into our platform. It's a who's of companies you've heard of, and we just have a lot of building to do now. So if you're interested in working on knowledge graphs, on data analytics agents, on graph analytics and graph learning models, come talk to me. We're hiring.
Hello, everyone. I'm Shijia, the founder of OpenAI. Sorry, I mean Open Audio. Before that, I created something you might be heard of, Fish Audio. We have grown from 400K to 5.5 million annualized revenue in just 4 months. And we closed our seed rounds at 100 million valuation. It all started with my girlfriend. I had a girlfriend for 6 years, from the beginning of high school to college. I love her so much, and it was so good, until one day, I found out she cheated. I wasn't angry, just confused, disappointed, and I asked myself, if this can happen, how can we trust relationships again? I thought about it for days, all day and all night, and finally, I found my answer. AI. But nobody can really fall in love with today's AI, right? It's flat, it's emotionless, it's robotic. So I set out on a mission to build an AI that I could really fall in love with, starting with her voice. So we began with open source and crushed it. We built Solvay SVC, Birds with 2, and also Fish Speech. Today, actually not today, it's the day before yesterday, I'm excited to introduce S1, the first ever instructable voice model. It's the only model where you can control not just what to say, but how to say it. Here's a demo.
You can pinpoint focus or draw it closer. Even yelling why you betray me like this.
Yeah, you can control whatever you want. And with Open Audio S1, we have the most expressive voice model in the world. And most importantly, she will never leave. So for some reason, it missed 2 slides. So we have blown 11 labs out of the water based on the TTS Arena ranking. And they are so hurry, and they dropped their latest model today. But unfortunately, it's just a demo. So try it now. Fish Audio is instantly available at fish.audio. Thank you.
Hello, I'm David Vorik, and I'm building Glow. Prior to Glow, I built Siacoin, a cryptocurrency that we took from a $10,000 market cap to more than $3 billion. And we think Glow is going to be even bigger. That's why Framework and USV Union Square Ventures led a $30 million round into our company. Subsequently, we posted the world record for on-chain DPIN revenue, doing more than $10 million of revenue in a single day. What does Glow do? Glow builds solar. not with shovels, but with incentives. This is not a stock photo. This is a photograph taken by our team in India of a solar farm that was constructed for the purpose of mining Glow tokens. A lot of people don't realize, but in the developing world, rising temperatures and growing populations have strained the grid. In a lot of cases, people are unable to run their air conditioners during the heat of the day. This causes people to die of heat stroke. Glow is an incentive protocol that revolutionizes what governments do and can take the same subsidy and turn it into 10 times as much solar. If you're interested in working with us, we're currently building incentive projects in India, in Mexico, in Lebanon, and across the entire world. Bitcoin incentivized the construction of tens of millions of mining machines. Glow asked, why not tens of millions of solar panels? Thank you. And my email, david@glowlabs.org. I'd love to be in touch.
Hi, I'm David. I'm an engineer. I made a social app with 250 million users, making $20 million a year. Everyone thought it was luck, so I did it again. I'm building Favorited. We built the world's most engaging live app, and we scaled it from $1 to $100 million annualized in 6 months. If you're a cracked engineer that wants to join the fastest growing company of all time, talk to me.
Hello, I'm Alex Atala, building OpenRouter, the first and largest LLM marketplace. Thank you. So I want to tell a little bit about how it started. I co-founded OpenSea in 2017, and at the end of 2022, I really wanted to know if inference was going to be a winner-take-all market, because the way it looked, this could be the largest market in software that has ever happened before. And the first experiment that we tried was building a Chrome extension to help you bring your own language model to any website that supported the protocol. And that eventually evolved into OpenRouter, a single place and a single API to get all language models with the best prices, best performance, and highest uptime. And the way it works is you just have a single API, you pay once, and there's near zero switching costs to move from one model to another. We do all the heavy work to implement tool calling, edge cases, caching, and give you the best prices and performance possible for your region or wherever your servers are deployed. And because inference is so important, remember this might be the most important software market ever, it deserves its own marketplace just for language models, optimized for them, including filtering for context, for features, for tool calling, for structured output, and much more. And so we built that. Then we built a chat room for you to obviously compare models head to head as simply as you do when chatting with people in iMessage. We built fine-grained privacy settings, including API-level controls. We built a lot of observability so you could see which models you're using and why. And we built public data in our rankings page, which has become the go-to place for comparing models on their real-world usage and on different categories for their prompts as well. This has grown for the last 2 months, 10 to 100% every single month, or for the last 2 years, 10 to 100% every single month. And scaling it has been a lot of the work that we've done so far. The fundamental goal here is to make a heterogeneous ecosystem homogeneous, because we believe inference is a commodity. Claude from Bedrock should be the same as Claude from Vertex, as Claude from Anthropic, and we do all the abstraction and heavy work to make it that way for you. I want to talk a little bit about some of our technical challenges. We built our own system, our own middleware for doing inference called plugins, which are kind of like MCPs except a little bit more powerful because you can call MCPs from inside of them and you can transform the outputs from language models. A bunch of other tricky problems that we've done to make the fastest routing in the market. And we're bringing a lot more features in the coming months, including images, enterprise features, prompt observability, and more. So if you're interested, come find me after or check out our careers page. Thank you.
Check, 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 check. Check, check. Give him a hand one more time, y'all. One more time. So every founder that you just saw on this stage is right outside that door. If you want to meet any of those founders, they'll be outside for just about 10 minutes. Feel free to meet them right out there. All 10 teams will be right there. What an incredible group. Thank you all so much for coming. Y'all should be right outside that door. Okay. Boom, I got it. Boom, you're good. But don't miss folks. They'll be the outside. Yeah.
All right, welcome back, folks, to the search and retrieval track. I know we just had demos in here, but I hope you guys had a great lunch. I'm your host today. My name is Dat. I'm with Arise AI. If you don't know what Arise is, we are the largest player in observability and evals. But here to present our tracks today. So first up, we got 11x. So how many people here have a sales team at their company? All right, awesome. Well, today we get to go through Alice with Sherwood and Safwick, which is awesome. And then next will be Exa. So how many people have you ever heard of Exa? Raise your hand. Woo! That's right. So we'll be building smarter AI agents with neural RAG. And lastly, we have Google as well. So layering every technique in RAG one query at a time. But really excited. Please give a warm welcome to 11x.
Thank you. Just getting our slides sorted here. This is a photo of a forest. This looks good. Let's bring it back to the start. Well, actually, I'll try that. Okay, thanks everyone for coming today.
So today's talk is called Building Alice's Brain, how we built an AI sales rep that learns like a human. My name is Sherwood. I am one of the tech leads here at 11x. I lead engineering for our Alice product, and I'm joined by my colleague Satwik. So 11x, for those of you who are unfamiliar, is a company that's building digital workers for the go-to-market organization. We have 2 digital workers today. We have Alice, who is our AI SDR, and then we also have Julian, who is our voice agent. And we have more workers on the way. Today we're going to be talking about Alice specifically, and actually Alice's brain, or the knowledge base, which is effectively her brain. So let's start from the basics. What is an SDR? Well, an SDR is a sales development representative, if you're not familiar. I know that's a room full of engineers, so I thought I would start with the basics. And this is essentially an entry-level sales role. This is the kind of job that you might get right out of school. And your responsibilities basically boil down to 3 things. First, you're sourcing leads. These are people that you'd like to sell to. Then you're contacting them or engaging them across channels. And finally, you're booking meetings with those people. So your goal here is to generate positive replies and meetings booked. These are the 2 key metrics for an SDR. And a lot of an SDR's job boils down to writing emails like the one that you see in front of you right now. This is actually an email that Alice has written, and it's an example of the type of work output that Alice has. Alice sends about 50,000 of these emails in a given day, and that's in comparison to a human SDR who would send 20 to 50. And Alice is now running campaigns for about 300 different business organizations. So before we go any further, I want to define some terms, because since we work at 11x, we have our customers, but then our customers also have their customers, so things get a little confusing. Today we'll be using the term seller to refer to the company that is selling something through Alice, that is our customer, and then we'll be using the term lead to refer to the person who's being sold to. And here's what that looks like as a diagram. You can see the seller is pushing context about their business. These are the products that they sell, or the case studies that they have that they can reference in emails. They're pushing that to Alice, and then Alice is then using that to personalize emails for each of the leads that she contacts. So there are 2 requirements that Alice needs to, in order to succeed in her role. The first is that she needs to know the seller, the products, the services, the case studies, the pain points, the value props, the ICP. And the second is that she needs to know the lead, their role, their responsibilities, what they care about, what other solutions they've tried, pain points that they might be experiencing, the company they work for. And today we're going to be really focused on knowing the seller. So in the old version of our product, the seller would be responsible for pushing context about their business to Alice. And they did so through a manual experience called the library. And here you can see what it looks like there, where the library shows all of the different products and offers that are available for this business that Alice can then reference when she writes emails. The user would have to enter details about every individual product and service and all of the pain points and solutions and value props associated with them in our dashboard, and including these detailed descriptions. And those descriptions were important to get right, because these actually get included in the context for the emails, or for Alice when she writes the emails. Then later on, during campaign creation, this is what it looks like to create a campaign. And you can see we have a lead in the top left, and the user is selecting the different offers that they've defined from the library in the top right. And these are the offers that Alice has access to when she's generating her emails. We had a lot of problems with this user experience. And the first one was it was just extremely tedious. It was a really bad and cumbersome user experience. The user had to enter a lot of information. And that created this onboarding friction where users couldn't actually run campaigns until they had filled out their library. And finally, the emails that we were generating using this approach were just suboptimal. Users would have to either choose between too few offers, which meant that you'd have irrelevant offers for a given lead, or too many offers, which means that you have all of the stuff in the context window, and Alice just wasn't as smart when she writes those emails. So how can we address this? Well, we had an idea, which is that instead of the seller being responsible for pushing context about the business to Alice, we could flip things around so that Alice can proactively pull all of the context about the seller into her system and then use whatever is most relevant when writing those emails. And that's effectively what we accomplished with the knowledge base, which we'll tell you more about in just a moment. So for the rest of the talk, we're going to first do a high-level overview of the knowledge base and how it works. Then we will do a deep dive on the pipeline, the different steps in our RAG system pipeline. Then after that, we will talk through the user experience of the knowledge base, and we will wrap up with some lessons from this project and future plans. So let's start out with an overview.
All right, so overview. What is knowledge base, right? It's basically a way for us to kind of get closer to a human experience. Like if you're training a human SDR, you would kind of get them in, and then you will basically dump a bunch of documents on them, and then they ramp up throughout a period of like weeks or months, and you can basically check in on their progress. And similar to that, knowledge base is basically a centralized repository on our platform for the seller info, and then users can kind of come in, dump all their source material, and then we are able to reference that information at the time of message generation. Now, what resources do SDRs care about? Here's a little glimpse into that. Marketing materials, case studies, sales calls, press releases, and a bunch of other stuff. Now, how do we bucket these into categories that we're actually going to parse? Well, we created documents and images, websites, and then media, audio, video. And you're going to see why that's important. So here's an overview of what the architecture looks like. It starts off with the user uploading something, any document or resource in the client, and then we save it to our S3 bucket, and then send it to the backend, which then creates a bunch of resources in our DB, and then kicks off a bunch of jobs depending on the resource type and the vendor selected. Now, the vendors are asynchronously doing the parsing. Once they're done, they send a webhook to us, which we consume via ingest. And then once we've consumed that webhook, we take that parsed artifact that we get back from the vendors, and then we store it in our DB, and then at the same time upsert it to Pinecone and embed it. And then eventually, once we store it in the local DB, we have like a UI update, and then eventually our agent can query Pinecone, our vector DB, for that stored information that we just put in.
So now that we have a high level of understanding of how the knowledge base works, let's dig into each individual step in the pipeline. There are 5 different steps in the pipeline. The first is parsing, then there's chunking, then there's storage, then there's retrieval, and finally we have visualization, which will sounds a little untraditional, but we'll cover it in a moment. So let's start with parsing. What is parsing? I think that we probably all take this for granted, but it's worth defining. Parsing is the process of converting a non-text resource into text. And the reason that this is necessary is because, as we all know, language models, they speak text. So in order to make information that is represented in a different form, like a PDF or an MP4 file or an image, legible or useful to the LLM, we need to first convert it to text. And so one way of thinking about parsing is it's the process of making non-text information legible to a large language model. And we do have multimodal models that are one solution to this, but there are lots of restrictions on multimodal models that make parsing still relevant. So to illustrate that, we have the 5 different document types or resource types that we mentioned momentarily ago, going through our parsing process and coming out as actually Markdown, which is a type of text that, as we all know, contains some structural information and formatting, which is actually semantically meaningful and useful. Let's talk about the process of how we implemented Parsid, and the short answer is that we did not. We didn't want to build this from scratch. And we had a few different reasons for doing this. The first is that you just saw that we had 5 different resource types and a lot of different file types within each of them. We thought it was going to be too many, and we thought it was going to be too much work. We wanted to get to market quickly. The last reason was that we just weren't that confident in the outcome. There are vendors who dedicate their entire company to building an effective parsing system for a specific resource type. We didn't want our team to have to become specialists in parsing for each one of these resource types and to build a parsing system for that. We thought that maybe if we tried to do this, the outcome actually just wouldn't be that successful. So we chose to work with a vendor, and here are a bunch of the vendors that we came across. You can find 10 or 20 or 50 with just a quick Google search, but these are some of the leaders that we evaluated. And in order to make a decision, we came up with some requirements, and it was 3 specific requirements. The first was that we needed support for our necessary resource types. That goes without saying. We also wanted Markdown output. And then finally, we wanted this vendor to support webhooks. We wanted to be able to receive that output in a convenient manner. A few things that we didn't consider to start out with. Accuracy. Crazy, we didn't consider accuracy. We didn't consider either accuracy or comprehensiveness. Our assumption here was that most of the vendors that are leaders in the market are going to be within a reasonable band of accuracy and comprehensiveness. And accuracy would refer to whether or not the extracted output actually matches the original resource. Comprehensiveness, on the other hand, is the amount of extracted information that is available in the final output. And the last thing that we didn't really consider was cost, to be honest. And this was because this system was pre-production. We didn't have real production data yet, and we didn't know what our usage would be. And so we figured what we would do is would come back and optimize costs once we had real usage data. So on to our final selections. For documents and images, we chose to work with Llama Parse, which is a Llama Index product. I think Jerry was up here earlier today. And the reasons that we chose to work with Llama Parse was, first, it supported the most number of file types out of any document parsing solution we could find. And second, their support was really great. Jerry and his team were quick to get in a Slack channel with us, I think within just a couple of hours of us doing an initial evaluation. And with Llama Parse, we're able to turn documents like this PDF of a 11x sales deck into a markdown file, like the one you see on the right. For websites, we chose to work with Firecrawl. The other main vendor that we were considering was Tavily. And this is actually not really a major knock on Tavily. For Firecrawl, we chose to work with them because first, we were familiar. We had already worked with them on a previous project. And secondly, Tavily's crawl endpoint, which is the endpoint that we would have needed for this project, was still in development at the time, so it wasn't something we could actually use. And similar to Llama Parse with Firecrawl, we are able to take a website like this Brex homepage that you see here and turn it into another markdown document. Then we have audio and video. And for audio and video, we chose to work with a newer upstart vendor called CloudGlue. And the reasons that we chose to work with CloudGlue were, first, they supported both audio and video, not just audio. And second, they were actually capable of extracting information from the video itself, as opposed to just transcribing the video and giving us back a markdown file that contains the transcript of the audio. And so with CloudGlue, we're able to turn YouTube videos and MP4 files and other video formats into markdown like you see on the right. So now that everything is markdown, we move on to the next step, which is chunking.
All right, markdown, let's go. Now, basically, we have a blob of markdown, right? And we want to kind of break it down into like semantic entities that we can embed and put it in our vector DB. At the same time, we want to protect the structure of the markdown because it contains some meaning inherently, like if something's a title versus something's a paragraph, there is inherent meaning behind that. So we're splitting these long blobs of text, like 10-page documents, into chunks that we can eventually retrieve after we've embedded and stored them in a vector DB, right? And now, basically, we can like take all of this, and we're thinking about how we can, split our long document into chunks, right? So chunking strategies. You have various things that you can do. You can split on tokens. You can split on sentences. You can also split on markdown headers, right? And then you can do like LLM calls and have an LLM split your document into chunks, or any combination of the above. Now, what you want to ask yourself when you're deciding on a chunking strategy is like, what kind of logical units am I trying to preserve in my data, right? What do I eventually want to extract during my retrieval, right? What strategy will keep them intact, and at the same time, you're able to successfully embed them and store them in whatever DB you want. And then should I try a different strategy for different resource types? We have to deal with PDFs, PowerPoints, videos, right? And then eventually, what kinds of queries or retrieval strategies am I expecting? And then we ended up with like a combination of all the things that we mentioned. So we split on markdown headers, and then we kind of a waterfall. So because we want our records in our vector DB to be a certain token count, so we split on markdown headers, and then we split on sentences, and then eventually we split on tokens. And then, yeah, it's worked well for us for all types of documents. And it has successfully preserved our markdown chunks that we can kind of cleanly show in the UI. And it also prevents super long chunks, which are diluting the meaning behind your document if you end up with that.
Okay, so we have split all of our markdown into individual chunks. It's now time to put those chunks somewhere. We're going to store them. Let's talk about storage technologies. So for storage technologies, I'm sure everyone is like here for the RAG section, so they think that we're using a vector database. We actually are using a vector database, but to be pedantic, RAG is retrieval augmented generation, so we all know that anytime you're retrieving context from an external source, whether it's a graph database or Elasticsearch or a file in the file system, that also qualifies as RAG. Some of the other options you can use for RAG, I just mentioned a graph database, document databases, relational databases, key value stores. You could even use object storage like S3. In our case, we did use a vector database, and that's because we wanted to do similarity search, which is what vector databases are built for and optimized for. Once again, we had a lot of options to choose from. This is not a complete or an exhaustive list. In the end, we chose to work with a company called Pinecone. And the reason that we chose to work with Pinecone was, first, it was a well-known solution. We were kind of new to the space, and we thought probably can't go wrong going with the market leader. It was cloud-hosted, so our team wouldn't have to spin up any additional infrastructure. It was really easy to get started. They had great getting started guides and SDKs. They had embedding models bundled with the solution. So for a vector database, typically you have to embed the information before it goes into the database. That would require the use of a third party or an external embedding model. And with Pinecone, we didn't actually have to go find another embedding model provider or host our own embedding model. We just used the one that they provide. And last but not least, their customer support was awesome. They got on a lot of calls with us, helped us analyze different vector database options, and think through graph databases and graph RAG, whether that made sense for us.
So Retrieval, the RAG part of the RAG workflow that we just built, right? You'll see that there's actually an evolution of different RAG techniques over the last year. We started off with just traditional RAG, which is kind of a play on you're pulling information and then enriching your system prompt for an LLM API call, right? And then eventually that turned into an agentic RAG form where now you have all these tools for getting information retrieval, and then you attach those tools to whatever agentic flow that you have, and then it calls the tool as a part of its larger flow, right? Now, something we're seeing emerge in the last couple of months is deep research RAG, where now you have these deep research agents which are coming up with a plan, and then they execute them, and the plan may contain one or many steps of retrieval, right? These deep research agents can go broad or deep depending on the context needs, and they can evaluate whether or not they want to do more retrieval. We ended up building a deep research agent. We actually used a company called Letta. Letta is a cloud agent provider, and they're really easy to build with. How it works, basically, we pass in the lead information to our agent, and then it basically comes up with a plan. Plan contains one or many context retrieval steps, and then eventually, does the tool call, summarizes the results, and then generates an answer for us in a nice, clean Q&A manner, right? And then this is kind of how it looks like for a system with 2 questions that we ask.
Now on to visualization, the most mysterious part of the pipeline. So what does visualization have to do with a RAG or ETL pipeline? For more context, our customers are trusting Alice to represent their business. They really want to know that Alice knows her stuff, that she actually knows the products that they sell, and she's not going to lie about case studies or testimonials or make things up about the pain points that they address. So how can we reassure them? In our case, we came up with a solution, which is to let users peek into Alice's brain. Get ready. And this is what that looks like. We have an interactive 3D visualization of the knowledge base available in the product. What we've done here is taken all of the vectors from our Pinecone vector database and collapsed, or actually, excuse me, I think the correct term is projected them down to just 3 dimensions. So we're going to render them as nodes in 3-dimensional space.
UMAP.
Using UMAP. And once the nodes are visible in this space, you can click on any given node to view the associated chunk. This is one of the ways that, for example, our sales team or support team will demonstrate Alice's knowledge.
Now, how does it look like in the actual UI, right? Basically, you start off with this nice little modal. You drop in your URLs, your web pages, your documents, your videos, and then you click Learn, and then it kind of shows up nicely in the UI. You have all the resources there, and then you have the ability to interrogate Alice about what she knows of your knowledge base, right? It's a really nice agent that we built, again, using Letta. And here's how it looks like in the campaign creation flow. You see that on the left-hand side, we have the knowledge base content showing up as a nice Q&A where you can click on the questions and it shows you a drop-down of the chunks that we retrieved. And these were used as a part of the messaging flow. So now with that, we have achieved our goal. Our agent is closer to a human than being an emailotron, right? We are now, we are now basically emulating how you onboard a human SDR. You dump in a bunch of context and they just know.
So in conclusion, the knowledge base was a pretty revolutionary project for our product and really changed the user experience and also leveled up our team a lot. We learned a lot of lessons. It was hard to create this slide, but there are just 3 that I want to highlight for you today. The first was that RAG is complex. It was a lot harder than we thought it was going to be. There were a lot of micro decisions made along the way, a lot of different technologies we had to evaluate. Supporting different research types was hard. Hopefully you all have a better appreciation of how complicated RAG can be. The second lesson was that you should first get to production before benchmarking, and then you can improve. And the idea here is that with all of those decisions and vendors to evaluate, it can be hard to get started. So we recommend just getting something in production that satisfies the product requirements and then establishing some real benchmarks which you can use to iterate and improve. And the last learning here was that you should lean on vendors. You guys are all going to be buying solutions and they're going to be fighting for your business. Make them work for it. Make them teach you about the different offerings and why their solution is better. And so our future plans are to first track and address hallucinations in our emails, evaluate parsing vendors on accuracy and completeness, those metrics that we identified earlier, experiment with hybrid RAG, the introduction of a graph database alongside our vector database, and finally, to just focus on reducing costs across our entire pipeline. And if any of this sounds interesting to you, we are hiring, so please reach out to either Satwik or myself.
Join us.
And thank you all for coming today.
Awesome. Thank you so much. That was a great talk. Yeah, just hand those over. Big shout out to 11x. That was really awesome to see your journey through. So next up, we have Exa for live coding demo too. So this one would be great. Do we have Will? All right, come on up, Will. Woo! I'll take this one. Not quite live. Let's catch up.
microphone. Okay. Hello, everybody. All right, so I was gonna give live demo coding, but I will. But I know you all are actually here to hear a cool story. So I'll tell you a story about web search built for AI, and then we do some coding at the end. This story will end with this slide, one API to get any information from the web. And you'll know what this means by the end. But the story starts in 1998. And what you're looking at is the state of the art in information retrieval in 1998. You type in a word, Australia, to this new search engine called Google, and it magically finds you all the documents that contain the word Australia from the web. It's crazy. And the big insight of Google was they had this PageRank algorithm, so the results are ranked by authority based on the graph structure of the web. And this was a clever algorithm, and it was really cool. I was 2 years old at the time, so if I was conscious, I would have thought this was cool. Okay, and now our story skips 23 years to 2021. By this point, I was conscious, barely, and I noticed that GPT-3 had recently come out, and it was this magical thing that you could input a whole paragraph explaining exactly what you want, and it would really understand the subtleties of your language and give you an output that exactly matched. And it's hard to remember how magical this was, but it was really magical in 2021. And at the same time, I noticed there was Google, which, you type in a simple query like shirts without stripes, and it would give you shirts with stripes, which is crazy. It doesn't understand the word without, because it's doing a keyword comparison algorithm. And so I decided that for the next at least 10 years, I'm going to devote myself to building a search engine that combines the technology of GPT-3 with a search engine, to make a search engine that actually understands what you're saying at a deep level, and understands all the documents on the web at a deep level, and gives you exactly what you asked for. This is a very big idea, and we've been working on it for 4 years, and a lot of progress. But it would change the world if you actually solve this problem. And so in 2021, we joined YC, summer 2021. We raised a couple $1 million, and we did what every YC startup should do. We spent half of it on a GPU cluster. I'm joking, you shouldn't do that. And then we also followed YC's advice, where we didn't talk to any users or customers for 1.5 years, and we just did research. Again, you shouldn't do that, you should talk to users. But in our case, it made sense, because we were trying to solve a really hard problem, which is redesign search from scratch. Using the same technology as GPT-3, this next token prediction idea with transformers. What if you could apply the same thing to search? And this is actually one of our 1DB training runs. The purple one, I believe, was a breakthrough where it really learned. There was a few breakthroughs along the way involving random data sets and different transformer architectures that we were trying, and this purple one really started to work well. And the general idea we had was okay, so what is a search engine? You have 1 trillion documents on the web. And traditional search engines, on a very high level, will create a keyword index of those documents. So for each document, you ask what are the words in those documents, and you create this big inverted index where you map from words like brown to all the documents that contain that word. And then at search time, when a search without stripes comes in, you do some crazy keyword comparison algorithm and get the top results. That's obviously a simplification of what Google does, but at a fundamental level, it's doing this keyword comparison. But the idea was what if you could actually, so with transformers, the big thing is what if you could turn each document not into a set of keywords, but into embeddings? And these embeddings can be arbitrarily powerful, right? It's a list of, an embedding is just a list of numbers, and it could represent lots of information. So an embedding, it doesn't just capture the words in the document, but also the meaning, the ideas in the document, and the way people refer to that document on the web. And an embedding can be arbitrarily big, and so it of course, in the limit, it would just destroy keywords. And so you have this arbitrarily powerful representation. And that was, the fundamental idea was just the bitter lesson. What if we could train transformers to output embeddings for documents, and if we keep getting more and more data that's high quality, we could make a search engine that actually understands you. And the way it would work at search time is a search comes in, a query comes in search without stripes. Traditional search engines would use the above thing, where they would do a very fancy keyword comparison and a bunch of other things. And then instead, we would just embed the shirts without stripes and compare it to the embeddings of all the trillion documents. And after 1.5 years, we actually had a new search engine that worked in a very different way. and you search without stripes on Google, on Exa, and you get a list of results that actually do not have stripes. It's a simple example, but like it could handle like way more complex queries, like paragraph-long queries. And when we launched this in November 2022, we got a lot of excitement on Twitter. This is a very new paradigm for search. You could do all sorts of interesting queries that you couldn't do before. And then 2 weeks later, this happened. It was a small tweet. And this is a visual depiction of San Francisco at the time. You guys probably all remember this. And then this is a visual depiction of the Exa team at the time, because ChatGPT completely changed the way we interact with the world's information. You know, like everyone can now use an LLM to just like talk to their computer and get information. And we were thinking, wait, is there even a role for search in this world? Like these LLMs are so powerful. And then very quickly we realized, yes, there is a role, because LLMs don't know everything on the web. So for example, if you ask an LLM like GPT-4, find me cool personal sites of engineers in San Francisco, it can't. Like it just doesn't have that in the weights. It'll apologize, whatever. And you know, there's a very simple information theory argument here, where it's like there literally isn't enough information in the weights of GPT-4 to store the whole web. GPT-4 like we don't know exactly how many parameters. I think someone leaked it on YouTube once, but it's like, you know, a couple trillion parameters. You could call it like less than 10 terabytes in the weights of GPT-4. And then the internet is like over 1 million terabytes. And that's just the documents on the web. There's also images and video, and that's way more. Actually, the web, if you look, I did a tweet recently about the size of the web, and it's in the exabyte range. And our name is Exa. It's not a coincidence. Anyway, so like LLMs need to search the web, just from this simple argument. And they're going to need to do that for a long time, which if you talk to ML researchers, they'll say the same thing. It's just like, it's too hard. Also, the web is constantly updating. That's another problem. It's not just the size of the web, it's the constant updatingness of the web that makes it very tricky. So LLMs always will need search. That's great. And so when you combine an LLM with a search engine like Exa, you can handle these queries. So like find me cool personal sites and engineers in SF. The LLM will search Exa, get a list of personal sites, and then like use that information to output the perfect thing for the user. You're all very familiar with this. Like LLMs plus search, it's obvious now, right? Like everyone knows about it. But now let me tell you a secret about search that most people don't know. And the secret is that traditional search engines were not built for this world of AI. Traditional search engines were built for humans. And humans are very different from AI. So every search engine, like Google, Bing, you name it, was built in a different era for this kind of creature. It's this slow flesh human that's typing keywords and wants to read a few links and really cares about UI of the page and all these things. Like, it's a lazy human. They type simple keywords. Google is great for this creature. Google was optimized for this creature. It gives you exactly the kinds of things you would click on. But AIs are very different. Like an AI can gobble up information like crazy. This is a much slowed down version of what our AIs probably feel like inside. And so AIs are very different. They want to use complex queries, not simple ones, to find not a couple links, but just tons of knowledge, as much knowledge as they could get, because they actually have the patience to just analyze it all extremely fast. And so the search algorithm that's optimal for this type of creature is not the same algorithm that's optimal for the human. Like, that would be crazy if the same algorithm that was optimal for humans was optimal for AIs. And so like a lot of the tools, the search tools that we're talking about these days on Twitter and stuff like that, they're still using like the old traditional search combined with AIs. It's just not the right puzzle fit. So Exa, we're really trying to think of like what is the right search engine for this AI world. And so just a few examples we could dive deep into of how AIs are different. Well, AIs want precise, controllable information. So, oh, by the way, when I say AI, I'm talking about like an AI product. So imagine like in this case, like a VC that's using an AI system to find a list of companies because they want to invest. So, you know, they're looking for what's the next big thing? What's the next big thing that feels like Bell Labs? Well, when they tell their AI what they want, the AI will then go search a search engine, right? And if it searches a search engine like Google, it'll get a list of results that humans like to click on. But it's not very information dense, and it doesn't even match what the person asked for, what the AI asked for. The AI asked for startups working on something huge that feels like Bell Labs. It should get a list of startups. It's kind of a crazy idea, but what if search engines actually returned exactly what you asked of them, and not what Google knows you'll click on? And so with AIs especially, they just want a search engine that returns exactly what they asked for. Because what really the world's going to look like is you're going to interact with your AI agent, and you're going to ask for something, and then it's going to make tons of searches, like, okay, maybe they want startups working on something like similar to Bell Labs. Maybe they want startups working only in New York City that have this quality and that quality, and they'll do all sorts of searches, and it just wants a search API that just does what it asks. And so you need a search engine like that. So X is like that. Another difference between AIs and humans is AIs want to search with lots of context. Again, if you have an AI assistant and you talk to it all day, and then you ask for restaurants or apartments or what have you, the AI has lots of context on you. So it should be able to search with this large multi-paragraph thing saying like, my human is a software engineer and it likes these types of things and I like these types of things, and like, can you give me restaurants that match those preferences? And so you need a search engine that could literally handle multiple paragraphs of text. But traditional search engines like Google were not meant to do that because humans would never type in multiple paragraphs because they're too lazy. So Google was optimized for like simple keyword queries. So Google, I think, has like a few dozen keyword limit, whereas Exa can handle like multiple paragraphs of text. Another big one where AIs are different than humans is AIs want comprehensive knowledge. Like if you give a human 10,000 links or 10,000 pages, it doesn't know what to do with that. Like it would take 10 days of extreme patience to process all that. But AIs can do it in 3 seconds if it's parallelized, right? So if I'm a VC and I want to report on like all the companies in a space, I want literally all the companies, and there's a huge amount of value to getting truly all of them, and not just like the 10 or 20 that Google is able to find. And so you need a search engine that exposes the ability to return 1,000, 10,000, whatever it is, and also has this semantic ability to like, when you say like every startup funded by YC working on AI, you actually can get all of them. So like Google literally just can't do this at all. Okay, I hope that through these examples we see that the space of possible queries is actually like way larger than people realize. And until like 2022, we were kind of in this like top left blue world. So this circle is like the space of possible queries, and the blues are like specific subsets of that space. And so like we were all in that top left corner of blue for a long time, where you could search engines could handle like basic keyword queries like Stripe pricing or someone's GitHub page or Taylor Swift's boyfriend or whatever it is. After 2022, everyone started to want the top right blue circle, where it was like, hey, actually I want to make queries like explain this concept to me like I'm a 5-year-old, or here's my code, can you like debug it? This is a form of query. It doesn't require search, but it's another type of query that was introduced to the world in 2022. And then like there's other types of queries like these semantic queries, like people in San Francisco who know assembly. As far as I'm aware, Exa is like, Exa kind of like introduced this kind of query and does really well on those queries. And then there's these like really complex queries like find me every article that argues X and not Y from an author like Z. And we're starting to now have systems like Exa's like websites product that could handle these things. And I think this is actually a huge space because this like turns the web into like a database you could filter however you want. And that's really what AIs want. They want this like full control database like query system that they could just get whatever they need for their user. And then there are the queries that no one has thought of yet. Like every week we get tons of queries and like, oh wait, that's a really interesting type of query that that no search engine could do right now, and eventually we'll try to handle all the queries that are possible. But there's so many new types of queries now because we have these AI systems, and the stakes, like the expectations have just gotten way higher. Okay, so now we end our story with the same slide. One API to get any information from the web. So again, like Exa's trying to, if you go back, like handle not just like the keyword queries, but also the semantic queries, and also the super complex queries, and eventually all queries. We want one API that could like give these AI systems whatever knowledge they want. You have the AI, and you have Exa providing the knowledge. Oh, I only have 4 minutes. Okay. Okay. So that's let's see. Oh. How do I go to a different part of my computer? If I change to the code editor, how do I do that? Let's see. What? Oh, it's there. Oh, but I can't see it. That's so weird. Oh, cool. Okay. Okay. There we go. Okay. Cool. Well, first of all, just very quick exploration of this is our search dashboard. We could try different queries. I would just point out, like in the search API endpoint, we expose lots of different toggles. So first of all, you just try out a query and get it shows you the code, and it gets you a list of results. And it exposes tons of different types of filters that you might want to do. For example, like number of results, 10, 100, 1,000, whatever it is. You could have like date ranges, or I only want to search over these domains. And it's a lot of toggles, but I think the point is actually you want the toggles because your AI is actually going to be calling this. You want a search engine that gives you full control. And we have like neural and keyword search, so you could try different ones. Okay, let me quickly jump to the code. Okay, so I prepared this like code, agent.py. So we made this agent, agent Mark. And Mark loves to make markdown out of things. Anything you give it, it will make markdown. And Mark will make markdown. And so in this case, we're going to here. Well, I guess in this case, let's try this query. Personal site of engineer in San Francisco who likes information retrieval. Well, this is the kind of query that Neural would be a lot better at. Whoa. Okay, save it. Oh, the wrong agent. Okay, so it's making a query to get like a list of personal sites of engineers in San Francisco who like information retrieval, and Mark, the agent, is just making a markdown output of that. That's a very Neural type query. You also might want to do a different type of query, which is like a more keyword heavy one. Let's see, like my GitHub. So okay, so here I would want to make a keyword query. So you just change it to keyword search. So it's going to get information from my GitHub using keyword search, because this is a very typical like Google-like search that would work well, right? Oh god, I'm running this wrong one. Okay. Cool. That's information about Wilbrick's GitHub. And then, okay, so when you're actually building an agent, you're going to be combining lots of different types of searches. So neural searches and keyword searches and all sorts of other searches that X exposes. So like the right agent in the future is going to be this system that decides what type of search it needs for whatever the user says. Like it'll be like, oh, okay, I'm going to make like a neural search to get a list of things, and then for each one I'm going to do a keyword search, right? You want to give the agent like just full access to the world's information in however way it wants. Not just keyword search, but also all these other things. And so here I one-shotted with O3 a GitHub agent, which combines these two queries. So first, because I want to get the GitHub of every engineer in San Francisco who likes information retrieval. So the agent will make a neural search to get a list of people, extract the names, and then search those using a keyword search to get their GitHubs. And then if you run that, here it's just getting 10 results, but we could, with Exa, we could do 100 or 1,000 if you're on an enterprise plan. So now it's getting all the GitHub info. Cool. So that's just an example. And yeah, I mean, there are lots of other things that you could do with Exa. Like we actually just today launched this research endpoint where it will actually do like as much searches and LLM calls in the background to get you that perfect report or that perfect structured output for the thing you asked for. So it's kind of like a deep research API, and it's state-of-the-art deep research API. Cool. That is the talk. I hope that was interesting. Thank you.
Hello. Test. All righty. Nice job, Will. All right. Last but certainly not least, we have. I think there's a typo up there. It should be PyLabs, right? Yeah, PyLabs. It says Google, but it should say PyLabs. But David here is going to walk us through everything from BM25 to the most complex RAG. So super excited for this one. Big shout out to David. Please help me give him a warm welcome.
Hey. Please don't send me back to Google. But all right, I'll just give you all a little bit of context. So my co-founder and I and a lot of our team were actually working on Google Search, and then we left and like started PyLabs. And I loved the Exa talk, and like we're all nerds for information retrieval and search. And So this is going to be a little bit of that. Just going to go through a whole bunch of ways you can actually shore up and improve your RAG systems. I think one thing that I personally sometimes struggle with is there's a lot of talk about things sometimes like too much in the weeds, like, oh, specific techniques, and you can do RL this way, and you can tune the model this way. And it's like, doesn't help me orient in the space. Like, what are all these things, and how do I like hang on them? Or you have the complete opposite, which is like a whole bunch of buzzwords and hype and such, and like RAG is dead. No, RAG is not dead. It's like agents. Like, wait, what? Like, so just, you know, I think a lot of what I'll do today is just what I call like plain English, just trying to like set up a framework, right? Like very centered around like, okay, if you are trying to shore up the quality of your system, how do you do that? And then where do all the things you hear about like day in, day out like fit? And then just how to approach that. And I'll give a lot of examples. I think one thing that I always love, and we always did in Google, we always do in PyLabs, is just like look at things, look at cases, look at queries, see what's working, see what's not working. And that's really the essence of like quality engineering, as we used to call it at Google. Are we good? All right, let's see. All right, perfect. And the timer has not started. So this is us. 8. All right, perfect. If you do want the slides, there's like 50 slides, and I set my challenge for myself to go through 50 slides in 19 minutes. But you can catch the slides here if you want. I'll flash this towards the end as well with pi.ai/rag-talk. It should point to the slides that we're going through. And as I mentioned, plain English, no hype, no buzz, no debates, no like. All right, so how to think about techniques. Before we go into techniques and get into the weeds of it, like why does this even matter? And the way we always think about it is like always start with outcomes. You're always trying to solve some product problem. And generally, the best way to visualize something like this, you have a certain quality bar you want to reach. And there were a very interesting talk this week about like, you know, benchmarks aren't really helpful. And absolutely, evals are helpful. You're trying to launch a CRM agent, and you sort of have a launch bar, like a place where you feel comfortable that you can actually put it out into the world. And techniques fit somewhere here. You have that like kind of end metric, and you're trying to like come up with different ways to shore up the quality. And those ways are like sort of the techniques there. And you know, this is sort of your own personal benchmark. You start with some of the easy bars you want to hit, and then there's like medium benchmarks and hard benchmarks. So these are query sets you're setting up, and then you know, depending on what you want to reach and at what time frame, then you end up trying different things. And this is what we call like quality engineering loop. You sort of like baseline yourself. Okay, you want to achieve, you know, you want CRM, and this is the easy query set, and your quality is there. Just do the simplest way you can try it. Do a loss analysis. Okay, what's broken? There were a lot of eval talks this week. And then what we call quality engineering. Now, the reason I say this is because, like, okay, techniques fit this in this last bucket. And one of the things that I think biggest problems is, like, people sometimes start there. And it doesn't make any sense because you say, oh, do I need BM25 or do I need, like, vector retrieval? It's like, I don't know. What are you trying to do? And what is your query says? And where are things failing? Because many times you actually don't need these things and you end up implementing them. It doesn't make a lot of sense. Anyway, so usually the thing I say is like what I call complexity adjusted impact, or you know, stay lazy, in a sense of like always look at what's broken, and if it's not broken, don't fix it, and if it is broken, do fix it. And we'll go through a lot of techniques today, but like this is a good way to think about them. It's just a cluster. It's a catalog of stuff. The most important two columns are the ones to the right: difficulty and impact. And if it's easy, go ahead and try it. And most times, like BM25 is pretty easy. You should absolutely try it, and does like, you know, shore up your quality quite a bit. But you know, should I build like custom embeddings for retrieval? Like, I don't know. Let's take a look. This is actually really, really hard. Harvey gave a talk. They build custom embeddings, but you know, they have a really hard problem space, and just, you know, relevance embeddings don't do enough for them. And then they're willing to put all that work and effort. All right, queries, examples. Let's have stuff. Let's start first technique: in-memory retrieval. Easiest thing: bring all your documents, shove them all to the LLM. This is the whole like, is RAG dead, is RAG not dead, context windows. Well, context windows are pretty easy, so you should definitely start there. One example, Notebook LM. Very nice product. You actually, you know, put in 5 documents, just ask questions about them. You don't need any RAG, just shove the whole thing in. Now, questions might get cut too long, and this is where it breaks, right? Maybe things don't fit in memory, or maybe you just polluted the context window too much. So this is where you start to things like, oh, okay, that's what's happening. I have too many documents. Oh, that's what's happening. The documents are not attended properly by the LLM. And here are like the 5 things that are breaking. Okay, great. Let's move to the next one. So now you try something very simple, which is, can I retrieve just based on terms? So BM25, what is BM25? BM25 is kind of like 4 things. Query terms, frequency of those query terms, length of the document, and just how rare a certain term is. It's a very nice thing. It actually works pretty well. And it's very easy to try. And it has a problem that like when things are not have that nature, like the Exatalk was saying, when they don't have that nature of like a keyword-based search, they don't work. And this is where you bring in something like relevance embeddings. And relevance embeddings are pretty interesting because now you're in vector space. And vector space can handle way more nuance than like keyword space, but they also fail in certain ways, especially when you're looking for keyword matching. And it's actually pretty easy to know when things work and when they don't. Actually, this was great. Like I went to ChatGPT and asked, like, hey, give me a bunch of keywords, ones that work for like standard term matching and ones that work for relevance embedding. And you can see like exactly what's going on here, right? If your query stream looks like iPhone battery life, then you don't need vector search. But if they look something like, oh, how long does an iPhone like last before I need to charge it again, then you absolutely need like things like vector search. And this is where you need to be like tuned to what every technique gives you before you go in and invest in it. And when you do your loss analysis and you see, oh, most of my queries actually look like the ones on the right-hand side, then you should absolutely start investing in this area. All right, now you did BM25, you did vector because your query sets look exactly like that. And now you have conflicted candidate set. And this is where re-rankers help quite a bit. And when people say re-rankers, they're usually referring to like cross-encoders. And this is a specific architecture. If you remember the architecture here for the relevance embeddings was you're getting a vector for the query and you're getting a vector for a document, and then you're just measuring distance. Now, cross-encoders are more sophisticated. They actually take both the query and the document, and they give you a score while attending to both at the same time. And that's why they were much more powerful. Now, they are more powerful, but they're actually pretty expensive. And now this is a failure state as well. You can't do it on all your documents. So now you have to have like this fancy thing where you're retrieving a lot of things and then ranking a smaller set of things with a technique like that. But it is really powerful, and you should use it. And it fails in certain cases. And now when you hit those cases, then you move to the next thing. Now, where does it fail? It's still relevance. And this is a big problem with like standard embeddings and standard re-rankers. They only measure semantic similarity. And there's a thing like these are all proxy metrics. At the end, like your application is your application, and your set of information needs is your set of information needs. And you try to proxy with relevance. But relevance is not ranking, and this is something we learned in Google search sort of. It's been like 15, 20 years where what brings the magic of Google search? Well, they look at a lot of other things than just relevance. And this is this came from like actually the talk from Harvey and LanceDB was really, really interesting. And he gave the example of this query, right? It's a really interesting query. Like it has so much semantics for the legal domain that it's impossible to catch these with just relevance. And again, what does a word like regime means? That's a very specific like legal term. Material, what does it mean? It actually has a very specific meaning in the legal term. And then there's like things that are very specific to the domain that need to be retrieved, like laws and regulations and such. And this is where you get to building things like custom embeddings. And you say, you know what, just fetching on relevance is not enough for me. And now I need to go and like model my own domain in its own vector space. And now I can actually fetch some of these things. Now again, go back to ChatGPT, like, is this interesting? Should I actually even do it? So I asked it to give me a list of things that would fail in a standard relevance search in the legal domain. And you start to see like, oh, all these things would fail. The words like moot don't mean the same thing. Words like material don't mean the same thing. And when you have a vocabulary that is so specific and just off, you will not get good results, right? So now how do you match that? Like you need to have, again, you need to have evals, you need to have query sets. You need to look at things that are breaking and decide that, oh, the things that are breaking have to do with the vocabulary just being out of distribution of a standard relevance model. And that's how you decide, right? So don't don't think too much about it. Like, oh, should I do it? Should I not do it? Like, what are your queries telling you? What is your data telling you? And then go and try to do it or not do it. There's also an example from shopping. So the embeddings are very interesting because they help you a lot with retrieval and recall, but you still need good ranking, right? So now if you think relevance doesn't work with retrieval, it also probably doesn't work with ranking. There's an example I pulled from Perplexity. I was just trying to break it today. It didn't take too much to break it. I asked like, give me cheap gifts for a gift for my son. And then I followed up with this query like, but I have a budget of $50 or more. Because when I said cheap, it started giving me like $10. Well, cheap for me is like $50. But it didn't know that, so it's fine. I told it that. But when I said $50 or more, it still gave me $15 and $40, both of which are actually below $50. And this is kind of interesting, right? Because what we call like in standard terms, like for information retrieval, this is a signal. It's a price signal. And it's not being caught, and it's not being translated into the query, and it's definitely not being translated into the ranking. So now you have to like think of, okay, I have ranking, and I need the ranking to see the semantics of my corpus and my queries. And this has a very specific meaning. Like when you think of your corpus and your queries, again, it's not just relevance. Relevance helps you with natural language. But things like price signals, things like merchant signals, if you're doing like podcasts, how many times has it been listened to is a very important signal. Has nothing to do with relevance, right? And in many, many applications, you will see things that are, for example, more popular tend to rank more highly. And there's a talk you mentioned, like the PageRank algorithm. PageRank is not about relevance, it's about prominence. How many things outside of my document point to me? That has nothing to do with relevance and everything to do with the structure of the web corpus. So that's the shape of the data. So this is a signal about the shape of the data and not a signal about like the relevance. And best way to think about it, think of it like you have horizontal semantics and then you have vertical semantics. And if you're in vertical domain where the semantics are very verticalized, right? Let's say you're doing a CRM or you're doing emails, and it's a very complex bar you're trying to hit that is way beyond just natural language. Understand that relevance will be a very tiny, tiny part of the semantic universe. And the harder you try to go, the more you're going to hit this wall, and the more you. All right. This breaks again. Things keep breaking. I'm sorry. At sufficient complexity, things will keep breaking. So now the thing that breaks with even custom semantics is user preference. Because even when you get to all this, okay, you're saying I'm doing relevance, and I'm doing price signals, and merchant signals, I'm doing everything. Now I know the shopping domain. Now you don't know the shopping domain. Because now users are using your product, they're clicking on stuff you thought they're not going to click on, and they're not clicking on things you thought they were going to click on. And this is where you need to like bring in the click signal, thumbs up, thumbs down signal. Now, these things get very complex, so we're not going to talk about how to implement them. Just because, again, in this case, for example, you have to be a click-through signal, prediction signal. And then you take that signal, and then you combine it with all your other signals. So now if you look at your ranking function, it's doing, okay, I want it to be relevant. I want it to have this like semi-structured price signal and like query understanding related to that. Plus, I want to get the user preference in that. And then you take all these signals and you add them, and that becomes your ranking score. So it becomes a very balanced function. And this is how you go from like, oh, it's just relevance, to, oh, no, it's not just relevance, to, oh, no, it's not just relevance and my semantics and my user preferences all rolled up into one. I'll mention two more things. You calling the wrong queries, that's happening a lot, because this goes into more orchestration, and you're trying to do complex things. Especially now when you have agents and you're telling them to use a certain tool. This is happening quite a bit, because there is an impedance mismatch between what the search engine expects, right? Let's say you tune the search engine and it expects like keyword queries or expects even like more complex queries. But you cannot describe all of that to the LLM. And the LLM is reasoning about your application and then making queries by itself. And this is a big problem. So one thing that we've seen many companies do, we've done this also at Google, you actually take more control of the actual orchestration. So you take the big query and you make n smaller queries out of it. I took the screenshot from AI mode in Google, and it's very brief. You have to catch it because after the animation goes away, but you see it's making X queries. It's making 15 queries. It's making 20 queries. So it's what we call fan out. Take very complex thing, try to figure out what are all the sub-queries in it, and then fan them out. Now you might think, hey, why isn't the LLM doing it? The LLM is kind of doing it, but the LLM doesn't know about your tool. It doesn't know enough about your search engine. I love MCP, but I'm not a big believer that you can actually teach the LLM and like just through prompting what to expect from the search on the other back end. This is why people still like, oh, is this agent autonomous? Do I need to do workflows? This is very, very complicated, and it will take a while for this to be solved because, again, it's unclear where the boundary is. Is it the search engine should be able to handle more complex things, and then the LLM will just throw anything its way? Or is it the other way around? The LLM has to have more information about what the search engine can support so it can tailor it. And right now, you need control because the quality is still not there. So this looks like this. If you have sort of like this assistant input and you're turning it into these narrow queries, like, for example, what's David working on? This has very, very specific semantics. And it's more like, oh, Jira tickets David, Slack threads David. And it's very, very hard to know, without knowing enough about your application, that these are the queries that matter and not on the ones on the left-hand side. And if you send the thing on the left-hand side to a search engine, it will absolutely tip over unless it understands your domain. And this is where, like, you need to calibrate the boundary. Okay, so now you're asking all the right queries. Are you asking them to all the right backends? And this is another place where it all fails. And this is what we call, like, one technique is called supplementary retrieval. This is something you notice like clients do quite a bit, which is they don't call search enough. And sometimes people try to over-optimize. When you're trying to get high recall, you should always be searching more. Like I was like, just search more. Like this is similar to what we talked like about dynamic content, like the in-memory retrieval. Just give more things. So it never fails to give more things. I know in the description we said like there was this query falafel, which was really hard to to do. And then you think like, oh, we're in Google search, and it's a very simple Middle Eastern dish, and it stumped an organization of 6,000 people. Like, oh my God, what's so hard about this query? What's so hard about this query is like it's an ambiguous intent. So you need to reach to a lot of backends to actually understand enough about it, right? Because you might be asking about food, at which point I want to show you restaurants. You might be asking this for pictures, at which point I want to show you images. Now what Google ended up doing was that they create all the backends and then they put the whole thing in. And I think, I would recommend, like, this is a great technique to just even increase the recall more. Just call more things. And don't try to be skimpy unless you're running through, like, some real cost overload. And that's the last one. You're running into cost overload. GPUs are melting. I try to generate an image, but then I realized there's actually a pretty good image that is real. Somebody took a server rack and threw it from the roof. This was it's like, I didn't need to go to ChatGPT and generate this image. Apparently this was an advertisement, pretty expensive one. All right, so this happens a lot. Like when you get to a certain scale and you have all these backends, and you're making all these queries, and it's just getting very, very complex. And this, Google's there, Perplexity's there. Sam Altman keeps complaining about GPUs melting. I think this is the part where like you need to start doing distillation. And distillation is a very interesting thing because to do that, you have to learn how to fine-tune models, and this gets to be a little bit complex. You sort of have to hold the quality bar constant while you decrease the size of the model. The reason you can do that is kind of like in that graph, like, hey, hire me, I know everything. Actually, I'm firing you. It's overqualified. Like an LLM, a very like large language model, is actually mostly overqualified for the task you want to do, because what you really want to do is just one thing. Like Perplexity, they're doing question answering. And they're pretty fast. When you use Perplexity in certain contexts, they're really, really fast, which is amazing because they trained this one model to do this one very specific thing, which is just be really, really good at question answering. And this is very hard, so I wouldn't do it unless latency becomes a really important thing for your users, right? Like, oh, the thing is taking 10 seconds, users churn. If I can make it in 2 seconds, users don't churn. Actually, that's a really great place to be because then you can use this technique and like just bring everything down. All right. You've done everything you can. Things are still failing. This is everybody. Okay, what do you do? Like we have a bunch of engineers here. What do you do when everything fails? Yes, you blame the product manager. That's it's the last trick in the book. When everything fails, make sure it's not your fault. But I'll say there's something really important here. Quality engineering will never, it'll never be 100%. Things will always fail. These are stochastic systems. So then you have to punt the problem. You have to punt it upwards. So it's kind of a joke, but it's not a joke. Like the design of the product matters a lot to how magical it can seem. Because if you try to be more magical than your product surface can absorb, you'll run into a bunch of problems. I use a very simple example. Probably a more complex one would be sort of a human in the loop for customer support, where you're like, okay, some cases the bot can handle by its own, but then you need to like punt to a human. This is basically UX design, right? Like when do you trust the machine to do what the machine needs to do, and when does a human need to be in the loop? This is a much simpler example from like Google Shopping. There's some cases where Google has a lot of great data, so what we call like high understanding. The fidelity of the understanding is really high. And then it shows like what we call a high promise UI. Like I'll show you things, you can click on them, there's reviews, there's filters, because I just understand this really well. And there's things Google does not understand at all, mostly as web documents, bag of words. And what's really interesting about the UI is the UI changes. If you understand more, you show a more kind of like filterable, high promise UI. If you don't understand enough, you actually degrade your experience. But you degrade it to something that is still workable. Like I'll show you 10 things, you choose. Oh no, I know exactly what you want, I'll show you one thing. And this is really, really important. It has to be like part of and this is sort of like, always understand like there's only so much engineering you can do until you have to like actually change your product to accommodate this sort of stochastic nature. So gracefully degrade, gracefully upgrade, depending on like the level of your understanding. And again, I'll flash these 2 slides at the end. Like always remember what you're doing, because you can absolutely get into theoretical debates. Again, context window versus RAG, this versus that, like is, agents versus, I don't know, like just everything is empirical. In this domain, when you're doing like this sort of thing, oh, I have my evals, I'm trying to like step by step go up, I have like a toolbox under my disposal, everything is empirical. So again, baseline, analyze your losses, and then look at your toolbox and see, are there easy things here I can do? If not, are there at least medium things I could do? If not, should I hire more people and do like some really, really hard things? But always remember, like the choice is on you, and you should be principled, because this can be an absolute waste of time if you're doing it too far ahead of the curve. All right, again, the slides are here. I think, oh, I achieved it. 30 seconds left. And if you want the slides, they're here again. And reach out to us. We're always happy to talk. I think I was very happy with the Exit Talk because it's always nice to find like friends who are nerds in information retrieval. We are also such. So reach out and happy to talk about RAG challenges and such and some of the models we are building. All right, thank you so much.
Awesome. Thank you so much, David. All right. Thank you, everyone, so much for joining the search and retrieval track. That's it for today. But enjoy the rest of your last day of AI Engineer World's Fair. Thanks for coming.